What is the universe? The question we still cannot answer. The universe is everything that exists, the totality of space, time, energy, matter, physical laws, and everything we call reality. When we use the word universe, we're referring to the most comprehensive structure ever conceived by the human mind, an immeasurable whole that contains everything from the smallest atoms to the largest galaxy clusters, including all that we have not yet been able to observe. It is the frame for all things, from the birth of stars to the death of light, from the vibration of subatomic particles to the expansion of cosmic superstructures. And even after centuries of scientific advancement, we still don't have a simple or definitive answer to the essential question, what is the universe after all? The very idea of totality escapes ordinary language and challenges the limits of logical reasoning, because the universe is at once the stage, the characters and the play of existence itself. The universe is not just an empty space where things happen. It possesses dynamic properties, geometric structures and fundamental laws that have governed its evolution since the moment time began. Yet the unsettling truth is that the definition of universe changes as science progresses. In antiquity, the universe was the starry sky visible to the naked eye. For 19th century astronomers, it was limited to the Milky Way. Today we know there are hundreds of billions of galaxies, each with billions of stars, and that the visible universe stretches over 93 billion light-years in diameter. But that's only what we can detect, the observable universe. The rest, if it exists, remains hidden behind physical and theoretical barriers we may never overcome. Even the concept of everything that exists is problematic. Does it include only what lies within our space-time? What if there are dimensions beyond the ones we know? What if the universe is just one of many cosmic bubbles floating in a larger sea of parallel realities, as some multiverse theories suggest? These questions show that the universe, beyond being vast, is structurally mysterious. Modern physics attempts to define it as a space-time continuum that emerged in the Big Bang and evolves under the laws of relativity and quantum mechanics. But these definitions are bound by mathematical language and our inability to grasp the absolute whole. Thus, the universe is at once the most studied object in science and the greatest enigma of existence. Each new astronomical observation expands our understanding while adding complexity to the notion of what the universe is. The Hubble Space Telescope revealed distant galaxies formed when the cosmos was only a few billion years old. The James Webb went even further, reaching into the first moments of light. These images reveal a universe in constant transformation, filled with structures that defy current physics, like supermassive black holes that existed shortly after the Big Bang, or mature galaxies from a time they theoretically shouldn't exist. This forces us to reconsider what we know about the origin, shape, and content of the universe. It is not a static entity. It is a reality that expands, transforms, and perhaps even has boundaries that change over time. The very notion of reality becomes fluid when we study the universe. It may contain regions completely isolated from us, separated by such immense distances that light will never reach here. These regions are technically outside our observable universe, but still part of the total universe, if that term has any practical meaning. There is also the possibility that physical laws vary from one region to another, which would imply a universe with multiple flavors of reality. That's why many scientists have abandoned the idea of defining the universe as a single, fixed thing. Instead, they try to describe it through mathematical models that capture only a fraction of the whole. The universe, therefore, may be so vast and varied that any single definition is inevitably incomplete. This inability to define it absolutely is not a failure of science, but rather a revelation of how astonishing the reality we inhabit truly is. The universe is not an external object we observe from the outside, as if we were looking at a map. We are part of it. Made of the same atoms that swirl in stars, we obey the same physical laws that govern galaxies. So, understanding the universe is also understanding ourselves. The question, what is the universe, is not just scientific, it's existential. It reflects a human search for meaning, origin, and belonging. Maybe one day we will have a final theory that allows us to answer with precision, but until then, the universe remains a horizon in constant expansion, both outside and within us. The origin of time. Did anything exist before the Big Bang? The question of what existed before the Big Bang is one of the most unsettling in modern cosmology because it directly challenges how we understand time. According to the general theory of relativity, formulated by Albert Einstein in the early 20th century, time is not something absolute or separate from the physical universe. It is an integral part of the very fabric of the cosmos. This means that time, like space, had a beginning. And according to current cosmological models, that beginning occurred approximately 13 billion and 800 million years ago with the event we call the Big Bang. Therefore, asking what existed before the Big Bang might be a meaningless question within the limits of our equations, like asking what lies north of the North Pole. According to the standard cosmological model, the Big Bang was not an explosion in space, but an expansion of space itself. In its initial instant, the universe was extremely dense, hot, and compressed into a singular point where all known physical laws break down. This point, called a singularity, is more of a mathematical prediction than a tangible physical entity. It is at this singularity that time as we know it also emerges. This implies that time began with the Big Bang and that speaking of a before may have no logical meaning. However, this conclusion does not settle the matter. It merely marks the boundary where our current theories can operate. Some approaches in theoretical physics attempt to go beyond this boundary. Quantum gravity theories still in development, such as loop quantum gravity, suggest the universe may have undergone infinite cycles of expansion and contraction, like a cosmic heartbeat, where the Big Bang would not be an absolute beginning, but a phase transition. Another hypothesis considers a pre-Big Bang universe in a different state governed by unknown physics. In such a scenario, time might exist in a different form, perhaps with different directions, different metrics, or even as a dimension that only emerges after the organization of energy and matter. There is also the model of eternal inflation, which proposes the existence of a multiverse, where bubbles of universes constantly emerge from a primordial sea of energy. Our universe would be just one of those bubbles, with its own time beginning at the local Big Bang, yet embedded in a larger structure where time could take on other meanings or forms. This would imply that our before the Big Bang is actually another kind of reality, perhaps forever intangible. The challenge here is not just theoretical, but also empirical. There is no way to directly test these ideas, because any information prior to the Big Bang would be irretrievably lost or inaccessible to current physical observation. Even within mathematics, the concept of pre-Big Bang time can be represented in speculative models, such as the Hartley-Hawking metric, proposed by Stephen Hawking and James Hartley. In this model, time before the Big Bang would not exist as a continuous line, but rather as an imaginary dimension, similar to space. Thus, the universe would not have a sharp beginning, but a smooth origin, like the curve of a sphere's surface. This model removes the singularity and softens the beginning of time, but it requires accepting a four-dimensional geometry in which classical notions of before and after no longer apply. From a philosophical standpoint, the idea of time existing before time itself raises deep dilemmas. What does it mean to exist without time? How can we conceive of causality, change, or sequence without a temporal axis? These questions suggest that time might not be a fundamental property of the universe, but an emergent construction arising from deeper relationships between energy, space, and information. Some physicists, like Carlo Rovelli, suggest that time may be an illusion, a collective effect of quantum processes, and that the temporal flow we experience is merely an appearance created by thermodynamics and memory. Therefore, the origin of time is not only a physical problem, but also an epistemological boundary. Every investigation into the before the Big Bang reveals the limits of our language, our theories, and the very structure of human thought. Perhaps in the future, new theories or observational discoveries will offer clues about this hidden past. Or perhaps the Big Bang truly is the absolute threshold, the zero line of everything we can ever know. In either case, the origin of time remains one of science's greatest mysteries, a reminder that, even after billions of years of cosmic evolution, we still walk blindly through the unknown. What existed before the creation of space and matter? The question of what existed before the creation of space and matter directly challenges the foundational pillars of physics. That's because, according to our current understanding, space and matter are not separate entities. They emerged together with the universe itself. At the instant of the Big Bang, approximately 13,800,000,000 years ago, not only did matter come into existence, but also the space in which it could exist. Before that, there wasn't a void waiting to be filled. The void, the space, the field in which things are located, all of it did not yet exist. Therefore, asking what was there before is, in practice, a question that forces us to completely rethink concepts like time, locality, and existence itself. In the universe's initial state, all known physical properties were compressed into an unimaginable density, a point where temperature, energy, space, and time had no defined forms. Matter as we know it, atoms, particles, fields, did not yet exist. Classical physics breaks down at this extreme limit, and only hypotheses from quantum gravity theories attempt to suggest a possible prior structure. One such idea proposes that the universe passed through a state of pre-spatiality, where the dimensions we now call space were still condensed, or did not exist at all as physical categories. This suggests that space is an emergent property, gaining structure only after the initial expansion. Matter in turn forms out of energy as the universe cools down. During the first fractions of a second after the Big Bang, there was only a plasma of subatomic particles like quarks and leptons, bathed in extremely high-energy radiation. These particles only combined to form protons and neutrons after a few millionths of a second. Atoms emerged hundreds of thousands of years later, once the universe had cooled enough for electrons to bond with nuclei. In other words, for most of the early cosmos, matter had no defined structure. This reinforces the idea that matter is also a consequence of the universe's own evolution, not a pre-existing entity. Some more radical theoretical proposals suggest that before the creation of space and matter, there was a purely mathematical or informational state. Physicist Max Tegmark, for example, proposes that the universe is a mathematical structure, where relationships between abstract entities gave rise to the physical reality we know. In this view, space is not a place but a set of relations between elements. Other theorists propose that only quantum fluctuations existed in a primordial field, the so-called quantum vacuum. This vacuum, despite the name, is not empty. It contains a minimal and incessant amount of energy, capable of spontaneously generating particles and antiparticles. This concept leads to the hypothesis that the universe arose from one of these fluctuations, a random event, but one allowed within quantum laws. If we consider cyclic models of the universe, like Roger Penrose's conformal cyclic cosmology theory, what we call before space and matter, might have been the end of a previous universe. In this scenario, time has no absolute beginning, and the space-matter structure we know is simply the current phase of an eternal cycle of contraction and rebirth. This hypothesis eliminates the need for an absolute origin and transforms the creation of space into a recurring phenomenon. Even so, these ideas remain highly speculative, as there are currently no clear ways to test them empirically. Available observations reach back only to the moment when the cosmic background radiation decoupled from matter, and anything before that becomes increasingly difficult to extract. From a philosophical perspective, the absence of space and matter before the universe places the human mind before a conceptual void. How can one imagine nothing without falling into contradictions? If there was no space, then there was no place. If there was no matter, there were no bodies, no structures, not even particles. And if there was no time, then there was no before. This total absence cannot be conceived as a state, because the very concept of a state requires space for something to exist in. The only possible way to approach this idea is through mathematical constructions or symbolic narratives, ones that acknowledge their own limitation before the ultimate nature of the cosmos. What existed before the creation of space and matter may be a question we'll never answer with certainty. It may be that the universe spontaneously emerged from a prior state with no physical dimensions, or that our reality is just a layer within a more complex and hidden system. In any case, this mystery continues to remind us that every structure we see today, galaxies, stars, planets, bodies, and even human thought, was born from complete absence, a void so absolute that even the concept of a void didn't apply. From that, Space expanded, matter organized itself, and billions of years later, human eyes began to gaze at the sky and ask, how did it all begin? Dark matter, the invisible that holds galaxies together. Dark matter is one of the most mysterious and fundamental entities in modern cosmology. Although it has never been observed directly, its existence is necessary to explain several gravitational phenomena that defy classical physics models. The term dark matter does not refer to something visually dark, but rather to its invisibility. It neither emits, reflects, nor absorbs light, or any form of electromagnetic radiation. This makes it completely undetectable by traditional telescopes. Still, scientists estimate that about 85% of all matter in the universe is composed of this invisible substance, a quantity that vastly outweighs ordinary matter, made of protons, neutrons, and electrons, which form stars, planets, and living beings. The most robust evidence for the existence of dark matter comes from observations of galaxy rotation. When astronomers measure how fast stars orbit the galactic center, they expect the outermost stars to move more slowly, in accordance with Newtonian laws. However, they observe the opposite. Stars at the edges of galaxies rotate almost as fast as those near the center. This suggests the presence of an invisible mass distributed around galaxies, creating an additional gravitational field that keeps these stars bound. Without this invisible matter, galaxies would simply tear themselves apart under their own rotation. In addition, dark matter also reveals itself through the phenomenon known as gravitational lensing. According to the general theory of relativity, massive objects distort the space around them, bending the path of light that passes nearby. In various astronomical observations, scientists have detected light curvatures from distant galaxies that cannot be explained solely by visible mass in the way. This excessive distortion indicates the presence of large amounts of invisible matter shaping the geometry of space, even though it emits no light. Another area where dark matter's presence becomes evident is in the formation of large-scale structures in the universe. Cosmological simulations show that in order for galaxy clusters and cosmic superstructures to form, with the speed and density observed today, a type of matter is needed that interacts gravitationally but is unaffected by radiation. Dark matter, therefore, acts like a kind of cosmic skeleton, an invisible framework that attracts ordinary matter and accelerates the formation of structures during the universe's first billions of years after the Big Bang. Without it, the visible universe would be more rarefied, dispersed, and structurally unstable. Despite all this indirect evidence, the composition of dark matter remains unknown. It cannot be made of atoms or molecules like those of the visible world, as that would imply interactions with light and radiation. The most promising candidate particles are known as WIMPs, short for weakly interacting massive particles. These particles would have significant mass, but interact only through gravity, and possibly the weak nuclear force, which would explain their invisibility. Another possibility is axions, extremely light and elusive particles that could behave coherently on large scales. However, none of these particles have yet been detected in laboratory experiments, despite decades of international efforts. Some alternative theories attempt to explain the same gravitational effects without invoking dark matter, by adjusting the laws of gravity on cosmic scales. Among these proposals is MOND, modified Newtonian dynamics, which suggests a change in the gravitational equation to explain galactic velocities. However, such alternative models struggle to explain all observed phenomena, especially on the scale of galaxy clusters and in predictions of the cosmic microwave background. Therefore, the dark matter hypothesis remains the most widely accepted explanation within the scientific community for these anomalies. The search for dark matter continues to be one of the highest priorities in modern physics. Underground experiments like Xenont, located deep in mines to avoid interference, attempt to capture rare collisions between dark matter particles and ordinary atoms. Space observatories and particle accelerators also search for indirect signals of its existence. If one day it becomes possible to directly detect a dark matter particle, it would open a new era of physics, allowing us to understand a portion of the cosmos that has remained hidden until now. Until then, we continue to live in a universe where most of its matter remains invisible, a silent and massive presence that holds galaxies together, shapes space, and perhaps carries the deepest answers about the nature of reality. Dark energy, the force that makes the cosmos expand faster and faster. Dark energy is arguably the most enigmatic and dominant component of the known universe. It accounts for about 68% of the entire cosmic composition, far surpassing both dark matter and ordinary matter combined. Yet we still don't know exactly what it is. All we can say with some degree of confidence is that dark energy is associated with the acceleration of the universe's expansion, a mysterious force that acts against gravity and causes galaxies to move away from one another at an ever-increasing speed. This phenomenon was discovered at the end of the 20th century and completely revolutionized cosmology. Until then, it was believed that gravity had been gradually slowing the expansion of the universe since the Big Bang. What was discovered, however, was the opposite. The universe is not only expanding, it is accelerating, as if some invisible force were pressing space outward from within. The first solid evidence of this acceleration came from observations of Type Ia supernovae, conducted by two teams of astronomers in 1998. These supernovae function as cosmic standard candles because they have predictable brightness and can be used to measure cosmic distances with precision. By comparing the distance of these supernovae with their recession velocity, determined through the redshift of their light, scientists realized that distant galaxies were moving away faster than expected. This could only happen if some previously unknown form of energy was acting on a cosmic scale to drive that acceleration. Thus, the concept of dark energy was born, a term created to name this force that alters the geometry of space-time in a repulsive way, expanding it at an increasingly rapid pace. Dark energy should not be confused with a substance in the traditional sense. It is not made of particles, it does not form structures, and it does not interact with light or matter in any measurable way. Instead, it may be understood as a property of space itself, something that permeates every point of the cosmos, like a constant, imperceptible pressure. The simplest hypothesis is that dark energy is a cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Einstein originally added this constant to keep the universe in static equilibrium, but later rejected it when it was discovered that the universe is expanding. Today, this constant re-emerges as a possible explanation for dark energy, an intrinsic force of the vacuum that pushes space outward. Another possibility is that dark energy is a kind of dynamic field, similar to the fields known in particle physics. In that case, it would vary over time and space, with properties still unknown. Some theorists refer to this field as quintessence, evoking the ancient idea of a fifth element beyond earth, water, fire, and air. This hypothetical field could fluctuate in intensity and interact subtly with matter and radiation, producing effects that we are only beginning to model mathematically. Even bolder models suggest that what we call dark energy is actually a sign that our theory of gravity is incomplete on cosmic scales, and that a new physics is required to explain the behavior of the universe on a grand scale. The impact of dark energy on the evolution of the cosmos is enormous. If its effect remains constant or increases, it will lead the universe to a fate known as the Big Freeze. In this scenario, cosmic expansion continues accelerating indefinitely, pushing galaxies farther apart until their light disappears from our observable horizon. Stars will extinguish, planets will freeze, and the universe will end in a vast, cold, and lonely darkness, where even atoms will eventually disintegrate over trillions upon trillions of years. All of this would be driven by this invisible force that paradoxically we have never measured directly. Other alternative scenarios also exist, depending on the exact properties of dark energy, including the Big Rip, in which expansion becomes so intense that it would tear apart atoms themselves. But these models depend on variables we still do not understand. The investigation into the nature of dark energy remains active in observatories around the world. Projects like the Euclid Space Telescope from the European Space Agency and the Vera Rubin Observatory in the United States are being developed to map the distribution of matter and energy in the cosmos with unprecedented precision. These instruments may reveal clues about how dark energy has evolved over time and whether its behavior changes in different regions of the universe. At the same time, theoretical experiments aim to simulate different cosmological scenarios to predict observable signatures that could confirm or refute specific hypotheses. Dark energy, therefore, represents not just a scientific challenge, but a conceptual abyss. It redefines our understanding of the universe's destiny, the structure of space, and the fundamental forces of nature. In a cosmos where the invisible dominates the visible, this silent force reminds us that, despite all our progress, we still know very little about what truly governs the universe. Perhaps by understanding dark energy, we will also discover new ways of understanding space, time, and even the very concept of existence itself. The final fate of the universe. Big freeze, big crunch, or something new. The final fate of the universe is one of the most fascinating, and at the same time, most unsettling questions in modern cosmology. For millennia, humans have looked up at the sky and wondered how it all began. Today, with the advancement of science, we also begin to speculate how it might all end. The universe is expanding, and this has been confirmed by numerous observations since the 1920s. But it's not a simple expansion. It's accelerating, as if some invisible force, now known as dark energy, were pushing space to dilate more and more rapidly. This realization radically changes our perspectives on the cosmic future. Scientists currently work with three main scenarios: the big freeze, the big crunch, and the big rip. Each of these outcomes depends on the exact properties of dark energy, the total mass density of the universe, and the geometry of space-time. In the scenario known as the big freeze, the expansion of the universe never stops. Galaxies drift farther and farther apart until they become so distant they can no longer be seen, even with the most powerful telescopes. As the universe stretches, cosmic radiation becomes weaker and weaker, and new stars cease to form due to the lack of available matter. The stars that do exist will burn through their fuel and extinguish one by one. Black holes will dominate the cosmos, consuming nearby matter and slowly evaporating via Hawking radiation. Over trillions upon trillions of years, the temperature of the universe will approach absolute zero, and all complex structure will vanish. What remains is a dark, cold, and silent universe. This is currently the most widely accepted end scenario among cosmologists, as it aligns with observations indicating that dark energy behaves consistently over time. Another possibility is the Big Crunch, a kind of cosmic collapse. In this scenario, the universe's expansion is not eternal. Instead, it slows down over time until it halts completely and reverses course. Gravity, driven by a sufficiently high total mass density, would overcome dark energy and pull all galaxies back together. The universe would begin to contract. Stars, planets, and galaxies would collide, merging into an ever hotter, denser sea of matter and radiation. At the end of this process, all the matter in the cosmos would be compressed once again into a minuscule volume, perhaps into a new singularity similar to the one that birthed the universe. Although this scenario still has supporters, it has lost ground in recent decades due to mounting observational evidence that expansion is accelerating, not decelerating. A third scenario also exists, called the Big Rip. This hypothesis depends on an even more extreme form of dark energy, known as phantom energy. In this model, the expansion's acceleration not only continues but intensifies exponentially. At some point in the distant future, this force would become so intense that it would surpass all the fundamental forces. First, galaxies would be torn apart, then stellar systems, planets, molecules, and even atoms. The entire universe would be disintegrated into its most fundamental particles. Space and time would cease to have any meaning, as no structure would remain to support them. Although this possibility is considered more speculative, it cannot be completely ruled out, since the true nature of dark energy remains unknown. There are also less conventional ideas, such as cyclic models and oscillating universes. In some of these theories, the universe undergoes successive cycles of expansion and contraction, an eternal sequence of big bangs and big crunches. Each cycle would erase the information from the previous one, resetting the laws of physics with slight variations. Other proposals suggest that the universe could gradually transform into something entirely different, perhaps with new dimensions or physical laws, in a process known as a cosmological phase transition. These models, although elegant, face observational challenges and still lack strong empirical support. All of these scenarios share one common truth: the universe on some timescale will cease to be as we know it. Stars will die, galaxies will disperse, and cosmic structure will dissolve. whether into emptiness or collapse. Even if that future lies trillions of years ahead, it casts a quiet shadow over existence. The fact that we are here now, in a moment when the universe is young, structured, and vibrant, is a rare cosmic coincidence. We live in a privileged era, where light still travels between galaxies, stars still shine, and consciousness can emerge to ask, how did it all begin, and how will it end? Regardless of the final fate, that question connects us deeply to the nature of the universe. It reminds us that we are part of a grand, ephemeral, and irreversible process. Every atom in our bodies was forged in stars that will one day extinguish. The cosmos, in all its vastness, is not merely the stage where matter dances. It is the dance itself. And one day, the final note of that symphony will be played. In the frozen silence of the Big Freeze, the final collapse of the Big Crunch, or the absolute unraveling of the Big Rip. Is the universe infinite or finite, and what lies beyond it? The question of the universe's size, whether it is finite or infinite, is one of the most profound and puzzling in modern science. For centuries, humans have tried to understand whether the cosmos has an end, a border, a boundary beyond which nothing else exists. Today, based on astronomical observations and general relativity models, we know that the universe is expanding, and that this expansion occurs in all directions. This means there is no absolute center, no privileged point. But this expansion doesn't answer the essential question: does the universe have a measurable, limited size, or does it stretch forever in all directions? For now, the answer still escapes our ability to observe or fully comprehend. What we can observe is only a fraction of the whole, the observable universe, a sphere approximately 93 billion light-years in diameter, centered on Earth. This limit is not due to a physical edge, but to the universe's age and the speed of light. Because the cosmos is around 13 billion and 800 million years old, we can only see objects whose light has had time to reach us since expansion began. Furthermore, space itself expands, meaning that objects once closer are now much farther than their light suggests. But the total universe, that which exists beyond the observable, could be vastly larger, and this is where hypotheses begin. If the universe is finite, it may have a closed geometry, like the surface of a four-dimensional sphere. In this model, you could travel in a straight line and eventually return to your starting point without ever encountering a boundary. This idea may seem counterintuitive, but it is mathematically consistent and was proposed by Albert Einstein himself. In such a universe, space is positively curved by its own mass and energy, and finitude does not imply abrupt edges, but complete geometric closure. If the universe is flat or negatively curved, it may be infinite, stretching endlessly in all directions like an infinite sheet of cosmic paper. Recent observations of the cosmic microwave background suggest that the universe is flat, with a very small margin of error, which means that if it is finite, it is so vast that it appears infinite for all practical purposes. The greatest challenge lies in empirically testing these possibilities. We cannot see beyond the cosmic horizon, and current physics limits our ability to safely extrapolate. Moreover, space may have complex topologies such as a multi-dimensional torus, where directions connect in intricate patterns. In that scenario, finiteness or infiniteness is not measured by physical edges, but by mathematical structures that are difficult to visualize. There are also theories that propose the universe is finite in volume, but without boundaries, like a video game where exiting through the right edge of the screen makes you reappear on the left. Space wraps around itself, creating infinite continuity within a finite structure. And what lies beyond the universe? That question assumes the universe is inside something greater, like a bubble floating in an external environment. But modern physics tells us the universe is space-time itself, not something contained within a larger realm. Outside of it, in a literal sense, there may be no space, no time, no physical laws. Still, some cosmological hypotheses, especially those involving the multiverse, suggest that our universe may be just one of many coexisting realities. These other bubbles could have different physical laws, varying dimensions, and independent histories. We do not interact directly with them, but subtle effects, such as patterns in the cosmic microwave background, might indicate collisions or influences between neighboring universes. The idea of multiple universes forces us to re-evaluate the notion of finiteness entirely. If our universe is just one element in an infinite ocean of universes, then the question of its size dissolves into an even more abstract scale. In that case, the universe could be finite but the multiverse infinite, or both could be finite but cyclical, like endless expansions and collapses within a larger space-time. Another possibility is that the visible universe is part of a fractal structure, where what we see replicates at ever larger scales, indefinitely, never encountering an edge. Modern cosmology therefore operates at the edge of the measurable. We use equations, models, and observations to construct coherent hypotheses, but we have no direct access to regions beyond the observable universe. Still, these speculations are far from empty. They help us form more refined questions, design more sensitive experiments, and reflect on humanity's place in a reality that may be infinitely greater than anything we've imagined. If the universe is finite, it is a perfectly structured mathematical miracle. If it is infinite, then we are immersed in a boundless vastness, where every point is as central as any other. In either case, human consciousness is a spark of perception in an incomprehensible ocean of space and time. The multiverse. Are we just one of infinite realities? The idea that our universe might be just one among many is one of the boldest and most fascinating concepts in contemporary physics. Known as the multiverse hypothesis, it proposes that the cosmos we know, with its galaxies, stars, particles, physical laws, and fundamental constants, may be just a small fraction of a far greater reality composed of multiple universes coexisting in parallel. These universes could have different origins, distinct geometries, varying numbers of dimensions, and even completely divergent physical laws. The notion of the multiverse did not arise as philosophical speculation, but as a mathematical consequence of several modern theories in physics, such as cosmic inflation, quantum mechanics, and string theory. In inflationary cosmology, for example, the idea of a multiverse arises naturally. This theory describes a phase of extremely rapid expansion that occurred fractions of a second after the Big Bang. During this inflation, the universe expanded exponentially, stretching space-time far beyond the observable. Some models of inflation, such as eternal inflation, predict that while our universe stopped inflating and evolved into the reality we observe, other regions continued inflating indefinitely, generating new cosmic bubbles, where different universes are continuously formed. Each bubble would have its own Big Bang, its own physics, and its own cosmic history. Within this framework, our universe would be just one bubble among trillions, or even an infinite number of others, in a sea of realities in constant creation. Quantum mechanics offers another perspective. In the interpretation known as the many worlds theory, every time a quantum choice is made, for instance when a particle can follow two possible paths, the universe splits into two parallel versions, one where the particle took one path and another where it took the opposite. This happens for every quantum event at every instant. The result would be an unimaginably vast number of alternate realities, branching into every possible outcome. Every decision, every random event, every microscopic fluctuation would create a new universe with its own distinct timeline. If this interpretation is true, then there are versions of you living slightly different realities in countless parallel universes, some similar to ours, others radically strange. String theory, a leading candidate for unifying the fundamental forces of nature, also predicts the existence of a multiverse, but in an even more abstract way. For its equations to work, string theory requires a universe with up to 11 spatial dimensions. These additional dimensions are compacted at minuscule scales, invisible to our instruments. The theory predicts a vast landscape of possible solutions, known as the string landscape, with as many as 10 to the 500th power possible universes, a number so vast it defies imagination. Each of these solutions would correspond to a universe with its own unique physical properties, including different particle masses, fundamental forces, geometries, and cosmological constants. Thus, our universe would be just one specific configuration among a nearly infinite menu of mathematical possibilities. The existence of the multiverse, however, raises deep philosophical and epistemological questions. If these other universes are completely isolated from ours, with no causal interaction, and no detectable physical signals, how can we confirm their existence? Some scientists argue that a scientific theory is only valid if it can be empirically tested. Others contend that even without direct access, the multiverse is an inevitable consequence of theories that already make verifiable predictions in our universe. In that case, rejecting the multiverse would mean denying the full implications of models that have already proven accurate. Science, then, faces the challenge of dealing with realities that may forever remain beyond the reach of direct observation. Still, there are efforts to search for indirect evidence. Collisions between bubble universes could, in theory, leave imprints in the cosmic microwave background, such as small circular anomalies. So far, these anomalies have not been confirmed with certainty. Numerical simulations attempt to model these interactions and predict their observational signatures. Observatories like the Planck Space Telescope have been used to search for such evidence, but results remain inconclusive. Other researchers investigate whether the fundamental constants of nature might vary slightly across different regions of the visible universe, which could suggest transitions between distinct physical realities. The idea of the multiverse also touches on the anthropic principle, the question of why the universe has exactly the right conditions for life. In a multiverse containing trillions of different universes, each with varying properties, the existence of a universe like ours, where constants are precisely tuned to allow the formation of atoms, stars, and conscious organisms, would no longer be a coincidence but a statistical inevitability. Only in universes with such characteristics could life arise to ask the question. This approach is controversial, as it blends physics with probability and philosophy, but many scientists believe it offers a possible explanation for the fine-tuning of our cosmos. Ultimately, the multiverse is a frontier of human thought. It expands the scale of reality so dramatically that it redefines the very meaning of existence. If true, then everything we experience, feel, and build is just a small fragment in an infinite tapestry of possible worlds. Every star we see in the sky would be just a drop in an ocean of invisible universes. Even if we can never touch or directly measure these other realities, the fact that we can conceive of them already shows the strength and boldness of the human intellect in the face of the unknown. The geometry of space-time, the fabric that can bend and tear. The notion that space and time are not separate entities, but interwoven parts of the same cosmic fabric, profoundly transformed our understanding of the universe. This idea was formally introduced by Albert Einstein in the early 20th century with the formulation of the general theory of relativity. Rather than treating space as a static stage where events occur and time as an absolute flow that progresses uniformly for all, relativity describes both as dimensions fused into a continuous structure, space-time. In this four-dimensional geometry, 3 spatial coordinates and 1 temporal coordinate combine to describe the position and evolution of everything that exists. More than that, this structure can bend, deform, stretch, and even rupture, depending on the presence and motion of matter and energy. According to general relativity, gravity is no longer a force in the traditional sense, as Newton once proposed. Instead, it is the manifestation of the curvature of space-time caused by the presence of mass and energy. A planet orbits a star not because it is pulled by an invisible force, but because the star curves the space around it, and the planet follows the straightest possible path in that curved space, a path called a geodesic. This means the universe is not flat like a board, but a malleable fabric capable of warping under the weight of reality. The more massive an object is, the more it bends the surrounding space-time. Black holes, for example, are regions where this curvature becomes so extreme that not even light can escape. This dynamic geometry of the universe is testable and has been confirmed through numerous experiments. The deflection of starlight during solar eclipses, first observed in 1919, confirmed that light bends when it passes near massive bodies, exactly as predicted by Einstein. More recently, the detection of gravitational waves in 2015, caused by the collision of distant black holes, revealed that space-time can ripple like an elastic sheet, sending undulations through the universe at the speed of light. These waves were predicted by the theory, but could only be detected a century later with instruments of extreme precision. The geometry of space-time is therefore not a philosophical abstraction, but a real, measurable, and active physical entity. The possibility that space-time might tear, that is, suffer discontinuities or ruptures, is still an open question in theoretical physics. In certain extreme models, such as those involving black holes or the singularity of the Big Bang, the curvature of space-time becomes infinite, pushing the equations of relativity to their limits. At these points, known as singularities, the very concept of space and time loses its meaning. We do not yet know whether these singularities truly exist in nature or are merely failures in our mathematical models. Quantum gravity theories, such as loop quantum gravity or string theory, aim to describe what happens under these extreme conditions, where the geometry of space-time would no longer be continuous but granular, quantized at minuscule scales. On cosmic scales, the geometry of space-time also determines the fate of the universe. Depending on its total curvature, whether positive, negative, or zero, the cosmos may be closed like the surface of a sphere, open like a saddle, or flat like an infinite sheet. Recent observations indicate that the universe is practically flat, with very small margins of error. This suggests that even if it is finite, it is so vast that, for all practical purposes, it behaves as if it were infinite. This geometry affects not only cosmic expansion, but also the path of light, the behavior of dark matter, and the evolution of galaxies over billions of years. Additionally, some theories explore even more radical possibilities of space-time geometry, such as wormholes, hypothetical tunnels connecting distant points of the universe by bending space in a way that allows nearly instantaneous travel between regions separated by billions of light years. These cosmic shortcuts are mathematically valid solutions within relativity equations, but would require exotic physical conditions to exist, such as matter with negative density. Although there is no empirical evidence for their existence yet, they represent the boldest boundaries of thought about the universe's structure. Therefore, space-time is not a passive backdrop on which the universe unfolds. It is itself a dynamic agent of reality, responding to the presence of mass and energy, and in turn, determining how bodies move and how time flows. In a universe where even the vacuum is active, and where space can bend, ripple, and perhaps even tear, we face a reality whose deep structure we are only beginning to understand. Each step in this direction brings us closer not only to comprehending the cosmos, but also to redefining what it means to exist within it. Black holes, the space abysses that devour even light. Black holes are perhaps the most extreme and intriguing objects in the entire known universe. They are not merely dead stars, but regions of space-time where gravity has become so intense that nothing, absolutely nothing, not even light, the fastest entity in the cosmos, can escape. The idea of a body with gravity so strong it could trap light was initially proposed in the 18th century by thinkers like John Michel and Pierre-Simon Laplace. However, it was only with Albert Einstein's general theory of relativity that this possibility gained a solid mathematical foundation. Later, with the calculations of Carl Schwarzschild, the first exact solution for a black hole emerged, a spherical region with a central point of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which there is no return. The event horizon is an invisible layer that marks the point of no return. Any object that crosses this boundary, whether a spaceship, a star, or a beam of light, will be inevitably pulled toward the center, the singularity, where known physical laws cease to operate. In that region, the density is so high and the curvature of space-time so intense that the very concept of time becomes distorted. Time, for an external observer, appears to freeze at the horizon's edge, while for someone falling into the black hole, the descent occurs in mere seconds. This duality of perspectives is one of the most radical demonstrations of how gravity can affect space-time. Black holes form when very massive stars, those with at least 20 times the mass of the Sun, exhaust their nuclear fuel. Without the pressure to support their cores against gravity, the stars collapse inward. In extreme cases, this collapse is halted by no known force, resulting in the formation of a black hole. There are different types of black holes, classified by their mass. Stellar black holes with a few to dozens of solar masses, supermassive black holes, which reside at the centers of galaxies and can contain billions of times the Sun's mass, and intermediate black holes which are still being actively searched for by modern astronomy. There are also hypothetical primordial black holes that could have formed right after the Big Bang, with sizes ranging from microscopic to enormous. Despite their reputation as devourers of everything, black holes are not cosmic vacuum cleaners that indiscriminately suck in everything around them. If the Sun were replaced by a black hole of the same mass, Earth would continue orbiting it normally. The only difference would be the absence of light and heat. Gravitational force depends on distance and mass, and a black hole behaves in relation to its environment just like any other massive body. What makes black holes unique is what happens inside the event horizon, a region where classical physics can no longer clearly describe reality. The first direct image of a black hole's shadow was captured in 2019 by the Event Horizon Telescope, a global network of radio telescopes. The image of the supermassive black hole at the center of galaxy M87 revealed a ring of distorted light around absolute darkness, caused by light orbiting near the event horizon. This monumental achievement confirmed predictions of general relativity with stunning accuracy. More recently, an image was released of the black hole at the center of our own galaxy, the Milky Way, known as Sagittarius AC, with about 4 million times the mass of the Sun. These images do not show the black hole itself, but the gravitational effects it exerts on surrounding light and matter, a visual testimony of an invisible entity. Another fascinating area of study is accretion physics, that is, how matter behaves when falling into a black hole. Matter orbiting a black hole forms extremely hot and bright disks, called accretion disks, which emit radiation across multiple wavelengths, including X-rays. Relativistic jets, streams of particles launched at near-light speeds, can also emerge from the poles of these objects, powering active galaxies and quasars. Paradoxically, black holes, though invisible, can be among the most energetic sources in the universe thanks to the behavior of matter around them. Despite all this progress, the interior of black holes remains an absolute mystery. The singularity is a point where density and curvature become infinite, a sign that our current equations break down. A union between general relativity and quantum mechanics is needed to describe what really happens inside, but such a theory does not yet fully exist. Some theoretical models suggest the singularity could be smoothed by quantum effects, or replaced by a new phase of matter or spacetime. There are also speculations that black holes might connect to other parts of the universe via tunnels known as wormholes, or even led to other universes. But these ideas, while fascinating, remain beyond experimental verification. Black holes are, therefore, both windows and abysses. They allow us to test the limits of physical laws, explore regions of the universe where time and space are distorted in nearly unimaginable ways, and perhaps, in the future, better understand the secrets of the cosmos. Each discovery about them is a step toward the unknown, a slow, patient, and silent descent into the dark core of reality. The black hole information paradox. The black hole information paradox is one of the greatest unresolved dilemmas in modern theoretical physics. It arises from a direct confrontation between two foundational pillars of science, quantum mechanics and general relativity. According to relativity, any object that crosses the event horizon of a black hole is irretrievably lost. The information about its composition, whether a star, a spacecraft, or even a photon, disappears forever within the singularity. But according to quantum mechanics, such total loss of information is impossible. One of the most essential rules of quantum physics is that the information about a physical system can never be destroyed. It can be scrambled, transformed, but must always be preserved at some level. When these two premises are combined, the irreversible absorption of matter by black holes and the conservation of quantum information, a deep conflict arises that challenges the integrity of our most fundamental physical theories. The problem became more evident in the 1970s when Stephen Hawking discovered that black holes are not completely black. By applying principles of quantum mechanics to the extreme gravitational field near the event horizon, Hawking showed that black holes emit radiation, now known as Hawking radiation. This radiation does not originate from within the black hole, but rather from quantum fluctuations in the vacuum near the horizon, which create particle pairs where one falls in and the other escapes. As a result, The black hole loses energy and mass very slowly, and over almost unimaginable timescales, trillions upon trillions of years, it evaporates completely. The problem is that this radiation is thermal, meaning random, without any encoding of the original information that fell into the black hole. When the black hole disappears, the information it contains seems to vanish as well, violating quantum mechanics. This contradiction became known as the information paradox. It is an enigma that puts our unified understanding of the laws of nature into question. If relativity is correct in predicting the destruction of information, then quantum mechanics would be incomplete. If quantum mechanics is correct in preserving information, then our understanding of black holes needs revision. The paradox is not just a theoretical curiosity. It signals that something essential is missing in our model of the universe, something that consistently unifies gravity with quantum principles. Solving this paradox might mean discovering a new unified theory of physics. Over the decades, various solutions have been proposed. One of the most promising ideas comes from the holographic principle, based on the work of Gerard 't Hooft and Leonard Susskind. This theory proposes that all the information contained within a three-dimensional volume can be encoded on its two-dimensional surface. Applied to black holes, this means that the information of everything that has fallen into them would not be lost but stored on the surface of the event horizon, as if it were a hologram etched into a spherical shell. In this scenario, Hawking radiation would not be entirely random, but would carry in an extremely subtle way the encoded information. This would preserve the principles of quantum mechanics and resolve the paradox without requiring the destruction of information. Another approach is known as the firewall hypothesis, a more radical proposal suggesting that the event horizon of a black hole is not as smooth as relativity predicts. Instead, there would be a violent energy barrier, a kind of firewall, that destroys anything attempting to cross it. This idea tries to preserve the unitarity of quantum mechanics, but at the cost of violating the smoothness of space-time predicted by relativity. In other words, to preserve information, the event horizon would have to behave very differently from what we imagined, a difficult conceptual sacrifice. More recently, advances in theories such as loop quantum gravity, ADS-CFT correspondence, and quantum entanglement networks suggest that information may in fact gradually escape in Hawking radiation, though in an extremely scrambled form. These models explore deep connections between gravity, thermodynamics, and information theory. A notable example is the idea that quantum entanglement between the inside and outside of a black hole could allow the indirect retrieval of information, preserving both quantum structure and the integrity of space-time. Despite these proposals, no definitive consensus has been reached. Most physicists agree that resolving the information paradox will require a complete theory of quantum gravity, a framework still beyond our experimental reach. When discovered, this theory may not only solve the black hole enigma, but also offer new ways to understand time, space, matter, and even the origin of the universe itself. Meanwhile, the paradox remains a mirror reflecting human limitation in the face of ultimate reality, a reminder that black holes challenge not only our telescopes, but also our deepest principles about what it means to know something. White holes and wormholes, theory or future reality? White holes and wormholes are theoretical concepts that emerge as legitimate mathematical solutions to the equations of general relativity, much like black holes. However, unlike black holes, which have been observationally confirmed, white holes and wormholes still dwell in the realm of scientific speculation. They represent extreme possibilities of space-time, where the geometry of the universe bends and connects in ways that defy our intuition. Both concepts, though distinct, share a common trait. They are manifestations of the mathematical depths of relativity, suggesting that the universe may contain structures far more complex than anything we can directly observe. A white hole, in theory, would be the exact opposite of a black hole. While a black hole absorbs all matter and energy that crosses its event horizon, a white hole would expel everything from its interior, preventing anything from entering. It would be a region of space-time, where matter spontaneously emerges with no possibility of return. From the standpoint of relativity equations, the existence of white holes is symmetrical to that of black holes, as if they were time-reversed versions of each other. However, there is no observational evidence that white holes exist, nor are there robust cosmological models explaining how they could form. They are considered unstable, as any slight disturbance in their structure would likely cause them to collapse into ordinary black holes. Nevertheless, some theorists speculate that the Big Bang, the event that gave rise to our universe, may have been in some way analogous to a white hole. In this scenario, the visible universe would have emerged from a singularity that, instead of attracting matter, expelled it in all directions. This interpretation, though highly speculative, raises the possibility that white holes could exist in cosmological contexts we do not yet understand. There are also hypotheses that white holes might represent the final phase of completely evaporated black holes, a kind of gravitational rebirth where the trapped information is explosively released. However, these ideas remain beyond any current means of verification. Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures that would connect two distant points in space-time via a tunnel. They were first described in 1935 by Albert Einstein and Nathan Rosen as a solution to the equations of relativity. In their simplest form, a wormhole would link two regions of the universe, or even two distinct universes, by a shortcut through space. In theory, this would allow for travel across vast cosmic distances in relatively short times, or even enable time travel, depending on the geometry involved. However, wormholes require extremely exotic conditions to remain stable. For a wormhole to stay open, it would have to be sustained by a form of matter with negative energy density, something that, so far, has not been observed in nature in significant amounts. This exotic matter, with anti-gravitational properties, would violate the so-called energy conditions of relativity, challenging the foundations of classical physics. In some quantum models, such as those involving the Casimir effect, small amounts of negative energy have been observed in laboratory settings, but nothing close to what would be needed to stabilize a wormhole. Therefore, although wormholes are mathematically possible, the physics required to make them real remains out of reach. Despite these limitations, wormholes have captivated the interest of theoretical physicists, especially at the intersection of general relativity, quantum mechanics, and information theory. In 2013, a conjecture called ER-EPR, proposed by Juan Maldacena and Leonard Susskind, suggested that wormholes, ER from Einstein-Rosen, and quantum entanglement, EPR from Einstein-Podolsky-Rosen, could be different manifestations of the same fundamental phenomenon. This idea seeks to unify the geometry of space-time with the structure of quantum information, indicating that the fabric of the universe may be entangled at levels far deeper than we imagine. If true, wormholes would not merely be hypothetical tunnels, but fundamental elements of microscopic reality. The possibility that white holes or wormholes might exist in the universe should not be hastily dismissed. The history of science shows that many ideas once considered absurd were later confirmed, such as the existence of atoms, gravitational waves, or the expansion of the universe. However, it's important to distinguish between theoretical possibilities and proven physical reality. For now, these structures remain elegant mathematical solutions, but unobserved. They serve as beacons on the horizon of knowledge, pointing toward directions where physics might yet evolve, even if we may never pass through one of these tunnels or witness the ejection of matter from a white hole. If we someday succeed in constructing a complete theory of quantum gravity, we may better understand whether these entities can actually exist. And if the answer is yes, they could radically transform the way we understand space, time, causality, and perhaps even consciousness itself. Until then, white holes and wormholes remain conceptual portals, not to other universes, but to the still unexplored regions of scientific imagination. The broken symmetry that originated everything. Why is there more matter than antimatter? One of the greatest mysteries in cosmology and particle physics is understanding why the universe is predominantly made of matter, rather than an equal mix of matter and antimatter. According to the fundamental laws of physics, each particle has a corresponding antiparticle with the same mass but opposite charges. The electron, for example, has the positron, the proton has the antiproton, and so on. These particles annihilate each other upon contact, releasing energy in the form of photons. When the universe came into existence, during the first instance after the Big Bang, the equations predict that exactly equal amounts of matter and antimatter should have been created. However, everything we see, stars, galaxies, planets, even our own bodies, is made of ordinary matter. Antimatter, although it can still be produced in accelerators and detected in high-energy events, virtually does not exist in large quantities in the observable universe. This raises a profound question. Why was this symmetry broken? What caused this imbalance at the very beginning of existence? This phenomenon is known as baryon asymmetry, the predominance of baryons, such as protons and neutrons, over their antimatter counterparts. For this asymmetry to arise, something in the laws of physics must have favored matter. In 1967, Russian physicist Andrei Sakharov proposed 3 fundamental conditions that must be met for the asymmetry between matter and antimatter to emerge in an initially symmetric universe. These conditions are violation of baryon number conservation, i.e., the possibility of creating more baryons than antibaryons, violation of C and CP symmetry involving particle-antiparticle exchange and spatial parity inversion, and the existence of processes outside thermal equilibrium, such as those occurring during phase transitions in the early universe. These conditions pave the way for the hypothesis that, shortly after the Big Bang, certain decays of heavy particles favored matter over antimatter, generating the imbalance we now observe. CP symmetry violation was first observed in 1964 in experiments with K-mesons, unstable particles made of quarks and antiquarks. Later, this phenomenon was also detected in B-mesons. These experiments demonstrated that the laws of physics do not treat particles and antiparticles the same way in all contexts, especially in weak interactions. However, the amount of CP violation observed so far is insufficient to fully explain the cosmic asymmetry. This suggests that some unknown mechanism, or new physics beyond the standard model, must be discovered to truly explain what happened during the universe's first moments. Some theories propose the existence of hypothetical particles much heavier than quarks and leptons, which would have existed only during the first trillionths of a second after the Big Bang. These particles, upon decaying, could have slightly favored the creation of matter. This process, known as leptogenesis, also involves the participation of heavy neutrinos and mechanisms that have not yet been directly observed. The search for these effects is one of the main motivations behind high-energy particle physics experiments, such as those conducted at the Large Hadron Collider, LHC. Other hypotheses include interactions with asymmetric background fields or cosmic phase transitions that irreversibly broke the symmetry. Another line of investigation involves the behavior of neutrinos themselves, particles with almost no mass that interact very weakly with matter. Current experiments aim to determine whether neutrinos and their antimatter counterparts, antineutrinos, behave exactly the same. If a difference is found between them, a CP violation in neutrinos, it could help explain part of the observed asymmetry. Large international experiments such as DUNE, Deep Underground Neutrino Experiment, and T2K in Japan have been specifically designed to investigate this type of violation with extremely high sensitivity. The absence of large regions of antimatter in the universe is also confirmed by astronomical observations. If entire galaxies were made of antimatter, we would expect to see intense gamma rays produced by collisions between matter and antimatter at their borders. However, no such signals have ever been detected. This reinforces the idea that the imbalance exists on both cosmic and microscopic scales, and that the origin of the asymmetry is not local but global, rooted in the universe's initial conditions. Thus, the broken symmetry between matter and antimatter remains one of the most profound enigmas in modern physics. It is not merely a theoretical curiosity, but an existential mystery. Without this slight imbalance shortly after the Big Bang, no stars would have formed, no planets would have emerged, and life itself would have been impossible. The universe, instead of being a stage filled with structure, would be a homogeneous void of radiation. The existence of something rather than nothing depends crucially on this microscopic asymmetry. Understanding how it arose may reveal not only new particles and forces, but also bring us closer to a deeper comprehension of why we are here. The enigma of time. Does it really flow the same for everyone? Time, so familiar and inescapable in human experience, is one of the strangest and most elusive entities in modern physics. Asking whether it flows equally for everyone might seem, at first glance, trivial. After all, one person's seconds appear to match another's. But when we examine time on the scales of the universe, extreme gravity and the speed of light, this notion of uniformity completely dissolves. Contemporary physics reveals that time is not absolute. It depends on gravity, relative velocity between observers, and the geometry of space-time. In other words, time is a flexible dimension, and its flow can stretch, slow down, or distort depending on the frame of reference. This realization, though deeply counterintuitive, is not only supported theoretically, but has been confirmed by experiments and high-precision observations. The special theory of relativity, formulated by Albert Einstein in 1905, was the first step in this conceptual revolution. It shows that the faster an object moves relative to an observer, the slower time passes for it, according to that observer. This phenomenon is known as time dilation. A classic example is that of the twins. One stays on Earth while the other embarks on a space journey at a significant fraction of the speed of light. Upon return, the traveling twin will have aged less than the one who remained. This effect is not just mathematical fiction, it has been measured. Atomic clocks placed on moving airplanes have shown minimal but measurable differences compared to identical clocks kept on the ground. At extreme speeds, such as those reached by particles in accelerators, this dilation becomes even more pronounced, allowing unstable particles to live far longer than they would at rest. The general theory of relativity, published by Einstein in 1915, went even further by showing that time also depends on the presence of mass and the intensity of the gravitational field. The stronger the gravity, the slower time passes. This phenomenon is known as gravitational time dilation. It means that time flows more slowly near massive objects like black holes than it does in more distant regions. A clock placed near the Earth's surface ticks slightly slower than an identical clock placed aboard a satellite in orbit. This effect is so real that it must be corrected in satellite navigation systems like GPS, which rely on extremely precise clocks. Without this correction, location errors would accumulate within minutes and render the systems completely ineffective. But what is time really? Is it a real entity that flows like a river, or just an illusion created by human consciousness? Physics still lacks a definitive answer. In many fundamental equations, such as those of quantum mechanics and relativity, time has no preferred direction. The laws are symmetric. They work just as well if time is reversed. Yet in the real world, we experience time as an arrow. It moves from past to future, and never the other way. This temporal asymmetry is generally attributed to the second law of thermodynamics, which states that entropy, the measure of disorder, always increases with time. This trend toward disorder creates our experience of the passage of time, but does not explain why time exists or why it has a direction in the first place. Some deeper theories question whether time, as we conceive it, is a fundamental property of the universe or an emergent construct. Certain proposals suggest that time might arise from the ordering of observable events, a kind of statistical illusion emerging from the relationship between quantum states. In other words, time might not be a real thing that exists by itself, but rather a consequence of how systems evolve and interact. This view, though radical, is gaining traction among physicists seeking to unify gravity with quantum mechanics. Models like loop quantum gravity attempt to describe space-time as a network of discrete events, where time is not continuous but granular, emerging only on macroscopic scales. Furthermore, experiments with entangled particles, those that remain connected even across vast distances, suggest that events can occur without a clear temporal order. In some recent quantum experiments, the order of two actions appears to be undefined, as if the concepts of before and after become malleable at microscopic levels. This challenges not only classical physics, but also our intuition about causality, memory, and perception. If time is not a continuous flow but a sequence of relationships between events, then our entire understanding of past, present, and future could be a subjective construct dependent on the universe's structure and the observer's frame. In light of all this, the question, does time flow the same for everyone, must be answered with a clear no. Time is relative to velocity, gravity, frame of reference, and even observational scale. It stretches, contracts, and possibly dissolves at deeper levels of reality. Modern physics invites us to abandon the idea of time as a uniform ruler and consider it as an elastic, sensitive, and perhaps even illusory dimension. Yet despite all scientific advances, time continues to flow. No matter how deeply we study it, it always escapes us, surrounds us, and transforms us. Planck's constant and the limits of the smallest possible scale. Planck's constant, symbolized by the letter h bar, is one of the fundamental quantities in modern physics, representing the transition point between classical physics and quantum mechanics. Its value is incredibly small, about 6 quintillionths of a trillionth of a joule second. In absolute terms, it's a minuscule number, but conceptually, it carries immense weight. Introduced by Max Planck at the end of the 19th century to resolve the blackbody radiation problem, it eventually became the cornerstone of quantum physics. It marks the threshold where quantum effects begin to dominate, and the classical description of reality is no longer sufficient. Planck's constant appears in nearly every foundational equation of quantum mechanics, from calculating the energy of photons to expressing Heisenberg's uncertainty principle. But beyond its role in equations, Planck's constant also defines a fundamental scale of the universe, the Planck scale. This scale is composed of natural units based solely on universal constants: Planck's constant, the speed of light, and Newton's gravitational constant. From these we derive the Planck length, about 100,000th of a trillionth of a trillionth of a trillionth of a meter. The Planck time. The time light takes to travel that distance, roughly 500,000ths of a trillionth of a trillionth of a trillionth of a second, and the Planck mass, approximately 22 micrograms. These values represent the smallest intervals of space and time where the known laws of physics still operate coherently. Below the Planck scale, our understanding of nature simply breaks down. Current theories cannot describe what occurs at such dimensions. General relativity, which governs gravity, and quantum mechanics, which governs fundamental interactions, both collapse when applied simultaneously at these limits. This suggests the existence of a deeper layer of reality, still hidden beneath the observable fabric. Many physicists believe that a unified theory of quantum gravity, something we do not yet have, would be capable of describing the behavior of matter, space, and time at that scale. Planck's constant, therefore, acts as a conceptual boundary. Beyond it, we enter unknown territory where the notion of continuous space-time may no longer apply. In some theoretical interpretations, such as loop quantum gravity, space-time is quantized, that is, divided into minimal units, like a fabric made of microscopic grains. The Planck length would correspond to the pixel size of the universe. There would be no smaller space, nor any shorter time interval. This fundamental granularity would prevent distances from being subdivided infinitely, resolving many of the paradoxes and mathematical infinities that plague current equations. Similarly, string theory also involves Planck's constant in its framework. In it, fundamental particles are not dimensionless points, but vibrating strings with a length on the order of the Planck length. The vibrations of these strings determine the properties of elementary particles, and the very geometry of the universe is shaped by these oscillations. Planck's constant is also closely tied to the uncertainty principle formulated by Werner Heisenberg. This principle states that it is impossible to know both the position and velocity of a particle with arbitrary precision at the same time. The more precisely one is known, the less precisely the other can be determined. This uncertainty is not a technological limitation, but a fundamental feature of the universe, written into the fabric of reality. And it is Planck's constant that defines the scale of this uncertainty. On macroscopic scales, this imprecision is irrelevant. But in the realm of subatomic particles, it dictates the rules of existence. Finally, Planck's constant appears even in the modern definition of the kilogram. Since 2019, the unit of mass in the international system is based on a Kibble balance, which links mass to Planck's constant through extremely precise measurements of electricity and motion. This means that this fundamental constant is no longer merely a theoretical parameter. It now plays a practical role in how we define and measure the world around us. Planck's constant is, therefore, a bridge between the visible and the invisible, between the classical and the quantum, between what we know and what we still seek to understand. It marks a boundary, not the end of knowledge, but the threshold of the unknown. The Planck scale tells us that there is deeper structure in the universe, and to reach it, we need new ideas, new languages, and perhaps a new scientific revolution. Until then, it remains a silent signature of the cosmos, a constant reminder that even in the smallest intervals of space and time, the universe keeps its secrets with absolute rigor. Quantum physics and the mystery of wave-particle duality. At the heart of quantum physics lies a phenomenon so counterintuitive and profound that it still challenges our capacity to comprehend the ultimate nature of reality, wave-particle duality. This peculiar trait of matter and light states that under certain conditions, particles behave like waves, and under others, waves behave like particles. This is not a mere metaphor or a mathematical approximation. It is a measurable physical reality, demonstrated in countless experiments. This dual behavior does not depend solely on the object being observed, but also on the act of observation itself. It reveals the inseparable connection between the observer and the observed, between the experiment and the result. And perhaps that is why quantum physics feels so strange, so fascinating, and so revolutionary. Light, which for centuries was treated as a wave, capable of propagating through space, refracting, interfering, and diffracting, showed, at the dawn of the 20th century, behaviors that could only be explained if it were made of particles. The photoelectric effect, studied by Albert Einstein in 1905, demonstrated that when light strikes certain metals, it releases electrons. But the number of electrons emitted did not depend on the intensity of the light, but on its frequency. In other words, a brighter light was not enough, it needed the right frequency. This could only be explained if light were composed of discrete energy packets, photons. Einstein won the Nobel Prize for this discovery, not for his theory of relativity, but for showing that light, a classical wave, also behaves like a particle. But the true astonishment came with the double-slit experiments. In this experiment, a beam of particles, whether photons, electrons, or even atoms, is fired at a barrier with two slits. If no measurement is made, the pattern observed on the screen reveals interference fringes, characteristic of waves. This happens even when particles are fired one at a time. They appear to interfere with themselves, as if they were passing through both slits simultaneously. But if we place a detector to observe which slit the particle went through, the interference pattern disappears. The behavior changes. Instead of a wave, we see a distribution of particles. This transformation, caused by mere observation, is one of the most unsettling aspects of quantum mechanics. This phenomenon does not mean that the particle chooses a path or that the device physically alters the system. What happens is more subtle. The act of measuring forces the system to assume a defined state among the many possibilities described by the wave function. This function is a mathematical equation containing all the probabilities of where the particle might be, and it is what propagates like a wave. When a measurement is made, the wave function collapses into a single result, a position, an energy, a trajectory. Wave-particle duality, therefore, is not a simple dualism. It reflects the probabilistic nature of quantum reality, where objects do not possess definite properties until they are measured. This duality is not limited to light. Electrons, protons, neutrons, and even complex molecules like fullerenes, composed of dozens of carbon atoms, have shown wave-like behavior in controlled experiments. This means that wave-particle duality is a universal property of matter, present across all scales, although it becomes imperceptible at everyday dimensions. A planet also has a wave function, but it is so narrow, so concentrated, that its wave-like behavior is negligible. At the quantum scale, however, this duality dominates, transforming our understanding of what it means to exist and move. This understanding led to the development of technologies that are now part of modern life: lasers, semiconductors, magnetic resonance imaging, quantum computers. All of these applications rely on the precise manipulation of quantum systems where duality is present. Chemistry itself, with its bonds between atoms, depends on the wave behavior of electrons around nuclei, the stability of matter, the shape of atomic orbitals, the properties of elements. All of it arises from the constructive and destructive interference of the wave functions that describe interacting particles. Moreover, the mystery of duality has inspired various interpretations of quantum mechanics. The Copenhagen interpretation, developed by Niels Bohr, holds that the wave function represents our knowledge of the system, and that only upon observation does the system decide its state. The many worlds interpretation, proposed by Hugh Everett, claims that all possible outcomes actually occur, each in a different parallel universe. Instead of collapsing, the wave function branches. These interpretations are not merely philosophical, they aim to explain how quantum reality connects to the world we perceive. Wave-particle duality, then, is more than a curious phenomenon. It is the core of modern physics, a window into a reality where objects are not solid things, but probabilistic entities that manifest as particles or waves, depending on the context. When we observe, we do not merely see the world. We shape how it presents itself. And the deeper we delve into this dual behavior, the more we realize that nature is not made of certainties, but of possibilities, dancing silently at the edge of the invisible. Quantum entanglement, particles that communicate instantly. Quantum entanglement is one of the most fascinating and challenging phenomena in all of modern physics. It describes a condition in which two or more particles become so deeply connected that the state of one is instantaneously linked to the state of the other, regardless of the distance separating them. This means that by measuring a property of one particle, the other knows the result instantly, even if it is on the opposite side of the universe. At first glance, this behavior seems to violate the principle of locality, the idea that an object can only be influenced by its immediate surroundings. This led Albert Einstein to call entanglement spooky action at a distance, as it appeared to contradict relativity, which limits the speed of any interaction to that of light. Entanglement is a direct consequence of the rules of quantum mechanics. When two particles interact in such a way that their properties become interdependent, they enter a joint state, described by a single wave function. This wave function represents the entire system, not individual particles with separate properties. From that moment on, even if the particles are separated by kilometers or billions of light years, they remain correlated. When one property, such as spin, polarization, or position, is measured on one particle, the value of the other becomes immediately known, as if there were an invisible link between them. It's important to clarify that entanglement does not allow for faster-than-light communication. This phenomenon cannot be used to transmit messages instantaneously because the result of measuring one particle is always random. Only by comparing the data from both measurements do the correlations emerge. Therefore, there is no direct violation of relativity, but rather a profound rethinking of our notions of separability, causality, and reality. The connection between entangled particles is not a signal exchange. It is a mathematical unity, a single entity spread across multiple points in space. The phenomenon was first formalized in the so-called EPR paradox, a paper published in 1935 by Einstein, Boris Podolsky, and Nathan Rosen. In it, the authors argued that quantum mechanics was incomplete precisely because it allowed these non-local connections. They proposed the existence of hidden variables, undiscovered properties that would explain the results without resorting to non-local phenomena. For decades, this idea remained a respectable possibility. However, in 1964, physicist John Bell formulated a set of mathematical inequalities that could be experimentally tested to determine whether these hidden variables actually existed. Starting in the 1980s, tests of Bell's inequalities began to be conducted with extremely high precision. One of the most famous was performed by Alain Aspect in France, and it unequivocally demonstrated that quantum correlations between entangled particles could not be explained by local hidden variable theories. Since then, increasingly refined experiments have confirmed these predictions. In 2022, three physicists, Alain Aspect, John Clauser, and Anton Zeilinger, received the Nobel Prize in Physics for their pioneering work on quantum entanglement and its fundamental implications. Today, entanglement is not merely a philosophical phenomenon, it forms the foundation of an ongoing technological revolution. Quantum computing, for instance, uses qubits, the basic units of quantum information, that can be entangled with one another. This entanglement allows certain algorithms to run with efficiencies impossible for classical computers. Quantum cryptography also employs entanglement to create ultra-secure communication systems, where any attempt at interception automatically disrupts the quantum state and signals intrusion. Another application is quantum teleportation, not the transportation of matter, but the transfer of quantum states between spatially separated particles, which has already been demonstrated in laboratories with photons, electrons, and even small atomic systems. Beyond practical applications, entanglement has deep philosophical and ontological implications. It forces us to abandon the classical view of a universe composed of independent objects, with intrinsic properties that exist regardless of observation. Instead, quantum reality seems woven into a web of interdependence where parts only make sense within the whole. The idea of locality, that an event can only be affected by nearby events, must be re-evaluated. The notion of objective reality also becomes weaker, as properties only fully emerge in the act of measurement. Perhaps the most extraordinary aspect of quantum entanglement is that it reveals a hidden order in the universe, a silent connection between seemingly separate elements. It suggests that the universe is, at some fundamental level, indivisible, a single entity expressing itself in multiple forms and locations. Entanglement is not a flaw in the theory, but one of its purest signatures. And by studying it, we are not just exploring the limits of human knowledge, but touching the very fabric of reality. String theory. Is everything in the universe vibration? String theory is one of the most ambitious and complex proposals ever conceived in theoretical physics. It begins with a simple yet revolutionary idea. The fundamental particles of nature, such as electrons, quarks, photons, and gluons, are not zero-dimensional points, but one-dimensional tiny strings that vibrate at different frequencies. Each mode of vibration corresponds to a different particle, with its specific properties of mass, charge, and spin. Instead of viewing the universe as being made of indivisible balls, string theory invites us to see it as a cosmic symphony, where everything that exists, from light to galaxies, is the result of the vibrations of these microscopic strings, whose length is about the size of the Planck length, roughly 1/100th of a millionth of a trillionth of a trillionth of a trillionth of a meter. This conceptual shift carries a grand promise: to unify all the fundamental forces of nature into a single mathematical framework. Currently, physics operates with two major theories: general relativity, which describes gravity and the behavior of space-time on macroscopic scales, and quantum mechanics, which governs the interactions between subatomic particles at the smallest scales. Both are extremely precise within their domains, but are incompatible when applied simultaneously to situations such as the interior of black holes or the first moments of the universe. String theory emerged as a candidate to resolve this conflict, offering a model in which gravity and quantum mechanics coexist harmoniously. One of the most intriguing features of string theory is its requirement for extra dimensions. While our world seems to have three spatial dimensions, length, width, and height plus time, string models only work correctly in universes with 9 or 10 spatial dimensions, plus one temporal dimension. These extra dimensions would be compactified on minuscule scales, curled up into highly complex shapes known as Calabi-Yau manifolds. Though invisible to our senses and current instruments, these dimensions would be crucial in determining the properties of particles and the forces we observe in the three-dimensional world. The topology of these microscopic structures could influence, for example, whether the universe has electrons or neutrinos, whether there is symmetry among particles, and what the values of the fundamental constants are. String theory also predicts the existence of particles not yet observed, such as gravitons, the hypothetical carriers of gravity, which would be specific vibrational states of strings. This would make gravity not only compatible with quantum mechanics, but a natural consequence of the universe's vibrational structure. Moreover, the theory gives rise to more complex objects than strings, called branes, short for membranes, which can have 2, 3, or more spatial dimensions. Some versions of the theory suggest that our own universe could be a three-dimensional brane, floating in a space with more dimensions, and that other branes could coexist in that same space, invisible to us, yet capable of gravitational interaction. Collisions between branes could even give rise to events similar to the Big Bang. However, string theory still faces serious challenges. One of them is the vast number of possible solutions, estimated at around 10 raised to the 500th power, each representing a universe with different physical laws. This landscape of vacua makes it extremely difficult to uniquely and objectively predict the behavior of our specific universe. This has led to debates among physicists about whether the theory is truly scientific or an excessively flexible mathematical framework. Another problem is the lack of direct experimental evidence. Because strings are incredibly small, it would require a particle accelerator, with energies trillions of times greater than the LHC to detect them directly, far beyond current technological capabilities. Even so, string theory has produced remarkable conceptual advances, even outside the field of particle physics. It has influenced areas such as pure mathematics, cosmology, and black hole thermodynamics. A notable example is the ADS-CFT correspondence, discovered by Juan Maldacena in 1997, which establishes a bridge between gravity in a five-dimensional universe and a quantum theory without gravity in 4 dimensions. This surprising connection has been used to study systems as diverse as superconductors, quark-gluon plasmas, and even brain structures. String theory, therefore, has become a rich mathematical laboratory for exploring the depths of space, time, and information. If one day we can experimentally confirm the predictions of string theory, whether through the detection of gravitons, the observation of extra dimensions, or signatures in cosmological experiments, it would mark one of the greatest leaps in human thought since the scientific revolution. But even if we never directly detect its vibrating strings, the very fact that such an elegant and comprehensive structure could, in principle, describe all the particles and forces of the universe is already a monumental intellectual achievement. At the heart of this theory lies an almost poetic vision of the cosmos. Everything vibrates, everything resonates, everything sings, and the universe, in its deepest essence, may not be made of matter or energy, but of pure harmony. The anthropic principle. Was the universe made for us? The anthropic principle is one of the most provocative ideas in modern cosmology, not because it introduces new observational data, but because it proposes a new way of interpreting the universe around us. It starts with an apparently simple, yet profoundly philosophical observation. The universe we inhabit has exactly the right conditions to allow life to exist, especially intelligent life, such as humans. The fundamental constants of physics, like the electron's charge, the proton's mass, the strength of gravity, and the cosmological constant, among many others, appear to be extremely finely tuned. Small variations in any of these constants would render life impossible. If the strong nuclear force were just slightly weaker, atomic nuclei would fall apart. If it were a bit stronger, nuclear reactions in stars would be so intense that no complex structures could form. Why then do these constants have precisely the values we observe? The simplest version of the anthropic principle asserts that we shouldn't be surprised by this fine-tuning, because if the universe didn't have these specific conditions, we simply wouldn't be here to observe it. In other words, our very existence as observers imposes a kind of observational bias. We can only exist in a cosmos compatible with life. This approach is called the weak anthropic principle, and it does not imply any kind of teleology or hidden purpose. It merely acknowledges that among all possible universes, we can only observe one in which the existence of observers is possible. On the other hand, there are stronger and more controversial versions of the anthropic principle. The strong anthropic principle suggests that the universe must have properties that inevitably lead to the emergence of intelligent life. This idea can be interpreted in an almost metaphysical way, as if the universe somehow intended to produce consciousness. Some philosophers and physicists have proposed that this could point to an underlying structure of reality where consciousness plays a fundamental role, perhaps as one of the basic pillars of existence, alongside matter and energy. Although many scientists reject this view as speculative, it has gained attention in debates at the frontier of physics, philosophy, and cosmology. The discussion becomes more complex when connected to the multiverse hypothesis. If our universe is just one among trillions or an infinite number of others, each with different physical constants and natural laws, then the fine-tuning of our cosmos is no longer a mystery. It becomes a statistical necessity. In a vast number of universes, a few would inevitably have the right conditions for stars, planets, and life to form. We exist in one of those few universes because we couldn't exist in any of the others. This combination of the anthropic principle and the multiverse forms a powerful explanation for why everything seems so finely tuned. There's no need for purpose, only cosmic natural selection. However, this approach is not free from criticism. Many physicists argue that the anthropic principle is a form of circular reasoning. It explains the observable universe based on the existence of observers, but provides no physical mechanism for the fine-tuning. Others see it as a methodological limitation, since it is difficult to test experimentally. If we cannot access other universes to verify whether they have different physical constants, then the argument remains in the realm of philosophy rather than science. Still, it plays an important role. It forces us to consider the role of life and consciousness in the cosmos and the limits of what we can truly know. Interestingly, the anthropic principle also resonates with ancient views about the harmony between human beings and the universe. From early cosmologies to natural theology, there has been a recurring impulse throughout human thought to seek meaning in the fact that we exist. The anthropic principle, by translating that search into scientific language, reopens the discussion about humanity's place in the cosmic scheme. It doesn't prove that the universe was made for us, but it also doesn't rule out the possibility that the universe, in allowing for our existence, is unique in its capacity to generate consciousness and complexity. Thus, the anthropic principle remains a frontier idea, not exactly a testable theory, but rather an invitation to reflect. It reminds us that science not only measures and calculates, but also asks, why do the laws of physics have precisely the values that allow stars to shine, molecules to form, planets to stabilize, and conscious minds to emerge? Is the universe just one among infinite others, a product of chance and statistics? Or is there a deeper, still unseen order that connects the existence of life to the most intimate structure of the cosmos? The mystery of magical numbers in nature, the golden ratio, pi, e, and more. Amidst the complexity of the universe and the apparent chaos of nature, certain numbers repeatedly emerge as silent patterns that transcend disciplines, structures, and scales. These are not ordinary numbers, but mathematical constants that appear mysteriously in phenomena as diverse as the spiral of a seashell, the shape of galaxies, the architecture of flowers, internet algorithms, and even the structure of the human mind. Among these magical numbers, the golden ratio pi and the number e stand out, as if forming an invisible code upon which reality itself is built. This raises a compelling question. Why do these specific numbers occur so frequently, and what does their recurrence reveal about the nature of the cosmos? The golden ratio, or golden number, is represented by the Greek letter F, phi, and has an approximate value of 1.618. It arises when a line is divided into two parts, such that the ratio of the whole to the larger part is equal to the ratio of the larger part to the smaller. This proportion appears in nature in remarkable ways. In the arrangement of leaves around a stem, the number of petals on many flowers, the shells of mollusks, the spirals of galaxies, and even in crystal structures. These are not coincidences. In many cases, this ratio provides evolutionary efficiency, such as in the arrangement of sunflower seeds, where they follow logarithmic spirals based on the golden ratio to maximize space and light exposure. This number has also captivated art and architecture, consciously employed in classical and modern works like the Greek Parthenon and the proportions of the Mona Lisa. It conveys an instinctive sense of balance and beauty. Another universal number is pi, represented by the Greek letter p, with an approximate value of 3.144159. It expresses the ratio of a circle's circumference to its diameter and is present in all circular and spherical forms in the universe. But pi goes far beyond geometry. It appears in waves, vibrations, statistics, probability, and even quantum mechanics. It shows up in the normal distribution formula, Schrödinger's equation, and the description of orbital movements. Its presence is so widespread that mathematicians see it as a symbol of the deep mathematical structure of the universe. Pi is infinite, irrational, and contains within its endless sequence of digits the totality of all possible numerical combinations. Some even poetically claim that the entire history of humanity is somehow encoded in the digits of pi. The number e, the base of natural logarithms, is another fundamental constant in both mathematics and physics. Its approximate value is 2.71828. It emerges in any situation involving continuous growth or decay, compound interest, radioactive decay, population dynamics, heat diffusion, and the evolution of dynamic systems. In physics, it appears in equations that describe particle behavior, Fourier transforms, chaotic systems, and statistical thermodynamics. Like pi, E is irrational, infinite, and unpredictable, yet it is essential for describing natural processes with extreme precision. Its presence reveals that nature operates through continuous exponential patterns that stretch across vast scales of time and space. These numbers are more than mathematical curiosities. They offer clues that the reality we observe, from the growth of a plant to the rotation of a galaxy, follows fundamental structures. Modern science, in studying these constants, begins to sketch a mathematical backdrop upon which all of existence is inscribed. Theoretical physicists like Roger Penrose speculate that mathematics may not just be a tool invented by humans, but rather a language inherent to the universe itself. If this is true, then these magical numbers are not merely useful, they are constitutive elements of reality. Nature chose them because they are the only ones that allow for stability, coherence, and complexity. Moreover, fields like quantum physics and chaos theory reveal equally fascinating numerical patterns. The Feigenbaum constant, for instance, which appears in nonlinear dynamic systems, governs the transition between order and chaos. Its approximate value is 4.669, and it defines how chaotic systems double their bifurcations. In natural language processing and artificial neural networks, logarithmic patterns and statistical distributions also follow pi, e, or f. This suggests that these magical numbers are not confined to the physical world, but also pervade the realms of information, consciousness, and data structures. The persistent appearance of these numbers raises philosophical questions about the nature of knowledge and existence. Why does mathematics describe the physical world so well? Could the universe, at its core, be a mathematical system? Physicist Max Tegmark, for example, argues that reality doesn't just obey mathematical rules, it is a mathematical structure. In this radical view, magical numbers are not just descriptive tools, they are the very substance of the cosmos. Each time we rediscover them, we encounter a mirror of universal logic etched into the essence of matter, life, and mind. Why is gravity so weak compared to the other forces? Gravity, despite being the force that governs the motion of planets, controls the birth and death of stars, and holds entire galaxies together over billions of years, is actually incredibly weak when compared to the other fundamental forces of nature. To illustrate this disparity, consider that a simple refrigerator magnet can overcome the gravitational pull of the entire planet to lift a paperclip. The electromagnetic force, which governs interactions between charged particles, is about 10 nonillion times stronger than gravity, that is, a 1 followed by 36 zeros. This colossal imbalance, known as the hierarchy problem, remains one of the great unsolved mysteries in modern physics, and its explanation may conceal profound insights into the fabric of the universe. The four fundamental forces of nature are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The strong force holds atomic nuclei together, despite the electrical repulsion between protons. The weak force is responsible for certain types of radioactive decay. Electromagnetism governs all interactions involving electric charges and magnetic fields. All of these forces, except gravity, fit harmoniously into the standard model of particle physics, a theory describing how fundamental particles interact. Gravity, however, does not fit into this model. It is described by a completely different framework, Einstein's general relativity. This disconnection between the two theoretical systems makes gravity a particularly peculiar and challenging case. One of the most explored hypotheses to explain gravity's weakness involves the existence of extra dimensions. In some versions of string theory and in brain-world models like that of Randall Sundrum, the universe may have more than 3 spatial dimensions, but the forces of the standard model are confined to a 3-dimensional brain, the observable universe. Gravity, however, could extend across all dimensions, diluting its intensity across this larger space. In this scenario, gravity isn't inherently weaker than the other forces. It just appears to be because it is spread out in ways we cannot directly perceive. While elegant, this idea still lacks empirical confirmation. Another possibility is that gravity, by its very geometric nature, behaves fundamentally differently from other interactions. Whereas electromagnetism and the nuclear forces operate through the exchange of messenger particles, like photons, gluons, and the W and Z bosons, gravity has no confirmed mediator. The hypothetical particle that would carry the gravitational force is known as the graviton, which would have spin 2, implying unique propagation rules. The absence of a complete quantum description of gravity also prevents us from calculating its relative strength at microscopic scales, further obscuring our understanding of the hierarchy between forces. The hierarchy problem also appears in terms of energy scales. Electromagnetism and the nuclear forces act across energy levels ranging from hundreds of electron volts to trillions, while gravity becomes comparable only at energy levels close to the Planck scale, about 16 orders of magnitude above what current laboratory experiments can achieve. This suggests gravity might unify with the other forces only under extreme conditions, such as those in the early universe or inside black holes. But without direct access to such regimes, the pursuit of a unified theory that includes gravity remains one of the grand challenges of contemporary physics. Even more intriguing is the fact that, despite its weakness, gravity dominates the universe at large scales. This is because it is the only force that affects all particles with mass, without exception, and it is always attractive, unlike electromagnetism, which can attract or repel. So even though it is weak, gravity accumulates. The gravitational pull between two objects is never cancelled, only added. On cosmic scales, this property makes gravity the primary sculptor of the universe's structure. It forms galaxies, clusters, stars, and black holes. It also governs the expansion of the cosmos and is directly involved in issues like dark energy, large-scale structure formation, and the ultimate fate of the universe. Understanding why gravity is so weak may hold the key to a new revolution in physics. If we discover that its weakness stems from hidden dimensions, an energy-scale decoupling mechanism, or some deep symmetry we have yet to uncover, it could unveil new layers of reality. And if we succeed in quantizing gravity, overcoming the limitations of the current model, we may open the door to understanding extreme phenomena such as the origin of the universe, the interiors of black holes, and perhaps even time and space in their most fundamental forms. The fifth force of nature. Does it really exist? For much of the 20th century, physicists believed that the fundamental forces of the universe had been fully identified. Four interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were considered sufficient to explain all observable phenomena, from the motion of planets to the reactions inside atoms. However, in recent decades, a series of experimental anomalies and theoretical suggestions have begun to challenge this seemingly complete picture. An audacious possibility has emerged. What if there is a fifth fundamental force of nature, still undetected in a conclusive way, but silently acting behind the scenes of the cosmos? The idea of a fifth force is not new. It was proposed more explicitly in the late 1980s, when laboratory experiments suggested small deviations in the strength of gravity over very short distances. These initial results were later refuted, but they reignited interest in interactions beyond the known four. Since then, different versions of this hypothetical force have been considered. One of the most discussed ideas is a force that operates at very small scales or in specific domains, such as within atomic nuclei or mediating interactions with yet undiscovered particles, possibly those that make up dark matter. Recently, an experiment in Hungary attracted the attention of the scientific community. Researchers at the Institute for Nuclear Research in Debrecen observed an unexpected excess of electron-positron pairs during an experiment involving the decay of beryllium-8, suggesting the possible existence of a new force-carrying particle nicknamed X17. If confirmed, this particle would have a mass of about 17 megaelectron volts and would be a light, unstable boson, a potential indicator of a new interaction beyond the standard model. While the results require independent replication, they have reignited debate about the presence of a fifth fundamental interaction. The implications of a fifth force are profound. It could help resolve some of the biggest mysteries not explained by the known forces. For instance, dark matter, which accounts for around 85% of the universe's total mass, does not interact with light or conventional nuclear forces, only with gravity. A new force acting solely on dark matter particles could explain their peculiar behavior, their distribution in galaxies, and even their formation. This force might also have played a more prominent role in the early universe, influencing cosmic inflation, the emergence of the first structures, and the anisotropy patterns in the cosmic microwave background. Another line of investigation explores the possibility that this fifth force may relate to violations of fundamental symmetries, such as parity conservation or CPT symmetry. This would open the door to even more comprehensive theories, such as grand unification models or supersymmetry-based proposals, where new particles and forces emerge naturally from the mathematical fabric of the cosmos. In some of these models, the fifth force would be associated with a new scalar field, similar to the Higgs field, but with distinct properties, possibly even varying over time or depending on environmental density. Bolder speculations connect this hypothetical force to the very structure of space-time. In some scenarios from quantum gravity and string theory, what we perceive as additional forces may in fact be the effects of extra dimensions or hidden geometries that manifest only under certain conditions. In this context, the fifth force would not be a new interaction in the traditional sense, but rather an emergent phenomenon of something deeper, like an unknown curvature of space-time at microscopic scales. This would compel us to rethink even the very definition of what constitutes a force. Despite theoretical excitement, the experimental detection of a new force is extremely challenging. It must be subtle enough to have escaped previous observations, yet strong enough to leave a detectable trace under the right conditions. This demands instruments of the highest precision and rigorous control of variables. Particle physics, atomic spectroscopy, ultra-cold atom experiments, and even astrophysical observations are all being used to search for signals of this potential interaction. There is no consensus or confirmation yet, but there are hints and good reasons to keep looking. If the fifth force is confirmed, it would mean that our current understanding of nature is incomplete, and that hidden layers of reality still await discovery. Such a breakthrough would be comparable in impact to the development of relativity or the revolution of quantum mechanics. It would reignite the quest for a unified theory capable of explaining all known forces, and perhaps shed light on dark matter, dark energy, and even the origin of the universe itself. For now, the fifth force remains on the border between the real and the possible, a mathematical shadow that may one day reveal a new map of existence. The holographic universe. Are we living in a projection? The idea that the entire universe might be a holographic projection sounds, at first glance, like pure science fiction. Yet in recent decades, this hypothesis has gained growing respect among theoretical physicists, thanks to surprising mathematical discoveries suggesting that all the information contained in a region of space could be encoded on its boundaries, just like a three-dimensional hologram stores its information on a two-dimensional surface. This proposal, known as the holographic principle, radically shifts our understanding of reality. According to it, what we perceive as a three-dimensional universe might, in essence, be an emergent illusion stemming from data stored in two dimensions. Modern physics, by exploring the limits of gravity and quantum mechanics, is increasingly treating this idea not as metaphor, but as a serious possibility. The origin of this concept lies in studies of black holes. In the 1970s, physicist Jacob Bekenstein proposed that a black hole's entropy, a measure of the amount of information it contains, was proportional to the area of its event horizon, not its volume. Stephen Hawking, by calculating the radiation emitted by black holes, reinforced this idea by showing that these objects emit thermal radiation, implying that they have finite temperature and entropy. The unavoidable conclusion was that all of a black hole's information appeared to be inscribed on its surface. This discovery led to the broader proposal that this principle could be valid for the entire universe. The information of any volume of space could be encoded on its boundary. The most mathematical and powerful formulation of this idea came with the ADS-CFT correspondence, proposed by physicist Juan Maldacena in 1997. It describes an equivalence between two very different kinds of theories. On one side, a theory of gravity operating in a three-dimensional space with negative curvature, ADS, anti-de Sitter space. On the other, a quantum theory with no gravity operating in just two dimensions on the boundary of that space, CFT, conformal field theory. The correspondence suggests that everything that happens in the three-dimensional interior can be perfectly described by equations that live on its two-dimensional boundary. It's as if the contents of a globe were encoded in its shell. Although our universe is not exactly an ADS space, this correspondence was the first concrete demonstration that the holographic principle could work. If reality truly is holographic, it would mean that the three-dimensional space we experience is a kind of emergent projection. Particles, fields, matter, energy, all would be the result of manipulating bits of information on a more fundamental surface. This aligns with a growing trend in theoretical physics, the idea that information, not matter, may be the universe's most fundamental component. In this context, gravity too would be emergent, not a primary force, but a statistical effect resulting from the microscopic rearrangement of information. This idea echoes proposals such as Eric Verlinde's entropic gravity, which seeks to derive the laws of gravity from thermodynamic principles. The holographic principle also offers new ways to tackle old paradoxes in physics. One of the most famous is the black hole information paradox. When something falls into a black hole, its information seems to be lost forever, violating the principles of quantum mechanics. But if all the information is on the boundary, the event horizon, then it is never truly lost. The hologram ensures that the information is preserved even if its physical manifestation has vanished. This reasoning is so compelling that some physicists speculate that the entire universe may have a horizon where all its information is stored, a kind of cosmic contour encoding everything that happens within. However, it's important to emphasize that the holographic universe is still a hypothesis. There is no direct observational evidence yet that we live in a projection. What exists is a growing theoretical framework, full of mathematical consistency and compatible with what we already know about gravity and quantum mechanics. Several experiments, like the Fermilab holometer, have attempted to detect irregularities in space-time that would be signs of the hologram's granularity, but so far, the results have been inconclusive. Even so, the possibility continues to inspire physicists, philosophers, and even artists due to its transformative power. The idea that we might be living in a projection may sound unsettling, but it's also liberating. It forces us to reconsider the nature of space, time, and reality. If the universe is a hologram, then perhaps what we perceive as solid, continuous, and three-dimensional is merely a mathematical shadow of something deeper and more essential, something where the boundary is more real than the center, and where information is the foundation of everything that exists. The origin of ultra-high-energy cosmic rays. In the near-total silence of space, invisible particles race across the universe at speeds approaching that of light, carrying energy so colossal they defy everything we know about physics. These particles are known as ultra-high-energy cosmic rays, and their origin remains one of the greatest mysteries of modern astrophysics. Some of these particles carry energies exceeding 100 billion electron volts, or expressed differently, more than 160 billion times the energy generated in collisions at Earth's largest particle accelerator, the LHC. In more tangible terms, we're talking about individual protons or atomic nuclei, possessing the kinetic energy of a fast-moving tennis ball. How can something so small contain such power? And even more puzzling, where exactly do they come from? Cosmic rays were first discovered in 1912, when Victor Hess ascended in a balloon with radiation detectors and observed that radiation levels increased with altitude, indicating an extraterrestrial source. Since then, most of the cosmic rays detected have relatively low energy and are produced by known sources, such as the Sun, supernovae, and galactic events. But the ultra-high energy rays, those exceeding 10 trillion electron volts, cannot be explained by these common mechanisms. They are extremely rare, but when they collide with Earth's atmosphere, they produce showers of secondary particles that can be detected by massive observatories around the world, such as the Pierre Auger Observatory in Argentina. one of the largest scientific instruments ever built to study these cosmic entities. One leading hypothesis for the origin of these super-energetic particles involves cosmic events on a gigantic scale: active galactic nuclei, spinning supermassive black holes, hypernova explosions, relativistic jets from quasars, and even galaxy collisions. In particular, it's believed that the particles could be accelerated by plasma shocks within jets emitted by black holes, or within the turbulent magnetic fields of pulsars and magnetars. These extreme environments possess the necessary potential to accelerate particles across vast distances, effectively acting as natural particle accelerators scattered throughout the cosmos. But even these sources have limits. For a particle to reach the energy of the highest cosmic rays ever detected, it would have to be accelerated across distances of tens of thousands of light years, or alternatively, by magnetic fields billions of times stronger than any we know. Another fascinating possibility is that these particles originate from beyond the observable universe, perhaps spawned by interactions involving objects from the multiverse or by events occurring shortly after the birth of the cosmos. Some theorists suggest they could be relics of physical processes involving extra dimensions, cosmic brains, or even exotic particles outside the standard model of physics. Others propose that these rays could be signs of decaying superparticles associated with dark matter, or manifestations of violations of fundamental symmetries in the universe. These ideas, for now, remain in the realm of speculation, but they illustrate how the origins of these particles may have implications far beyond conventional astrophysics. There's a crucial detail: these particles do not travel in straight lines. As they move through space, they are deflected by interstellar and intergalactic magnetic fields, losing any directional trace of their source. This makes it extremely difficult to pinpoint where they came from. It's like trying to trace the path of a bullet after it has ricocheted countless times. Moreover, there's a theoretical limit known as the GZK cutoff, named after physicists Greisen, Zatsepin, and Kuzmin, which states that particles above a certain energy level will interact with the cosmic microwave background radiation and lose energy along the way. This implies that if we detect cosmic rays above this limit, they must have originated from relatively nearby sources, within 160 million light-years. However, when scientists map these directions, they don't find any evident sources with enough energy, which only deepens the mystery. The investigation continues, with new detectors, statistical techniques, and theoretical models. Experiments like the telescope array and ice cube are attempting to capture neutrinos and other correlated particles in hopes of tracing connections between different cosmic phenomena. The sky is continuously monitored for gamma-ray bursts, pulsars, or black holes in intense activity. Each detected event is cross-referenced with the arrival data of energetic particles. The hope is to find a match, a cosmic signature finally understood. But for now, ultra-high-energy cosmic rays remain anonymous messengers from the deep universe. Coming from unknown regions, traveling for billions of years, crossing magnetic fields and vast distances, they arrive as fragments of an undeciphered story. They remind us that no matter how much we know, the cosmos still holds surprises, and perhaps the most powerful of those surprises is heading toward Earth right now, carrying the energy of 1,000 suns. The cosmic microwave background, the echo of everything's birth. Imagine a sound that echoes eternally through the hallways of the universe, not an audible melody, but a primordial vibration, a thermal noise that fills the entire cosmos with an invisible signature. This silent sound is the cosmic microwave background, the oldest light we can observe, the lingering echo of the birth of everything. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, while attempting to calibrate a radio antenna, this radiation is a direct witness to the universe when it was still young, only 380,000 years old, a mere fraction compared to the 13.8 billion years that followed. Since then, studying this radiation has become one of the keys to understanding the origin, evolution, and structure of the cosmos. Before the emergence of the cosmic microwave background, the universe was a dense and opaque plasma composed of light particles, photons, electrons, and protons in constant collision. In this state, light could not travel freely. Each photon was continually absorbed and re-emitted by other particles, But as the universe expanded and gradually cooled, a moment came when electrons and protons combined to form the first neutral atoms, primarily hydrogen. This event, known as recombination, released the photons which could finally travel freely. From that moment on, the universe became transparent, and the photons from that original release are still traveling through space today, stretched and cooled by cosmic expansion. Today, this radiation is no longer hot or visible as it once was. It is extremely cold, about 2.7 degrees above absolute zero, or more precisely, 2.7255 Kelvin. This places it in the microwave spectrum, invisible to the naked eye but detectable by radio telescopes. Its distribution is remarkably uniform in all directions of the sky, with tiny temperature variations on the order of millionths of a degree. These minute fluctuations, detected by satellites like COBE-WMAP and Planck, contain precious information about the seeds of cosmic structure, slightly denser regions that would later give rise to galaxies, galaxy clusters, and ultimately everything that exists. These fluctuations are not random noise. They follow specific patterns that reveal details of the early universe. Studying these ripples has allowed cosmologists to determine the age of the universe, its rate of expansion, the amount of dark matter, and even the geometry of space-time. The cosmic microwave background is, in essence, a baby picture of the universe, frozen in time and carrying the fingerprint of its initial conditions. It is the most direct and irrefutable evidence of the Big Bang model, confirming predictions made decades before its detection. One of the deepest questions this radiation helps explore is that of cosmic inflation, a phase of exponential expansion believed to have occurred in the universe's earliest instance after the Big Bang. If inflation truly happened, it would have left subtle imprints on the polarization of the cosmic microwave background. Detecting these marks is one of modern cosmology's greatest goals, as it would allow us to directly access information from the universe's first trillionths of a second. Telescopes such as BICEP and the upcoming CMB-S4 are searching for these signatures with increasing precision. But beyond the technical science, there's something profoundly poetic about this radiation's existence. It is the whisper of a newborn universe, still resonating through time and space. By detecting its signals, we are literally listening to the first words of creation, not in human language, but in cosmic frequencies. The cosmic microwave background connects us to the common origin of all things, to a moment when there were no stars, no planets, no living beings, only a uniform sea of light, awaiting the first disturbances that would shape the destiny of the cosmos. It is proof that everything had a beginning, and that this beginning left behind traces we can still read, like archaeologists of time, probing the darkness with instruments of pure sensitivity. The fundamental constants. Could they be different? The universe, in all its complexity and vastness, seems to dance to the rhythm of a set of incredibly specific numbers. These numbers, known as fundamental constants, are the invisible gears that keep reality functioning with surgical precision. The speed of light, the gravitational constant, the charge of the electron, Planck's constant, the fine structure constant, among others, are values that do not change, at least within the limits of our measurements. Without them, there would be no atoms, no stars, no chemistry, no biology, and no consciousness. But what would happen if these constants were slightly different? And more intriguingly, who or what determined that these values should be exactly as they are? This seemingly simple question opens a chasm of possibilities and uncertainties where physics and philosophy intertwine. The fine structure constant, for example, is a pure number with no units, approximately 1 divided by 137. It determines the strength of the electromagnetic force acting between charged particles. If this value were slightly smaller or larger, atom formation would be compromised. A tiny deviation and chemistry as we know it would be impossible, and therefore life too. The same applies to the ratio between the masses of the proton and the electron, the gravitational constant that governs the weight of bodies, and the cosmological constant that drives the accelerated expansion of the universe. All of these quantities appear to be tuned with a precision that borders on the improbable. This coincidence has a name: fine-tuning of the universe. Scientists still do not know whether these constants are truly fixed, or whether they could assume other values in parallel universes, in different regions of the cosmos, or even across cosmic time. Some hypotheses suggest that they could vary on cosmological scales, but no measurable variation has been confirmed so far. The apparent stability of these constants, measured over billions of years using the cosmic microwave background, the light from distant quasars, and the abundance of primordial chemical elements, suggests that they are universal and immutable, at least within the observable universe. However, broader theories like string theory and multiverse models allow for the possibility that these constants are merely local. In other words, in other universes or cosmic bubbles generated by eternal inflation, the laws of physics could be entirely different. The fine structure constant could be 1 divided by 42 or by 1000. Gravity could be far stronger or weaker. Planck's constant could take another value. In some of these hypothetical universes, matter might not even clump together. In others, stars could explode before ever forming. Only in a tiny subset of such realities would the parameters be tuned to allow for the existence of complex life. This is the essence of the so-called anthropic principle. We observe this universe because it is one of the few, or perhaps the only one, where consciousness can arise. The question of the origin of these numbers directly touches the search for a theory of everything, a mathematical framework that would unify gravity with quantum forces and reveal from first principles why each constant has the precise value it does. However, such a theory has not yet been achieved. It is possible that some constants are accidental, emerging from broken symmetries, initial quantum fluctuations, or statistical patterns. Or perhaps they are required by some deeper mathematical necessity that we have yet to comprehend. Either way, the question remains, are these constants arbitrary or inevitable? Some experiments are underway to test for minuscule variations in certain constants. Telescopes and ultra-precise spectrometers examine the light of ancient stars, looking for deviations in the absorption of specific chemical elements. The ALMA mission in Chile, for example, has analyzed molecular clouds billions of light years away, searching for any sign of a change in the electron's mass. So far, the results reinforce the constancy of these values, but the margin of error still allows for very small variations that, if confirmed, would completely transform our understanding of space and time. Ultimately, reflecting on the fundamental constants is like contemplating a cosmic signature. They are the fixed notes of a symphony that never changes its key, but allows for an almost infinite variety of melodies. They are the mathematical backdrop upon which the tapestry of the universe unfolds. Whether these numbers are the product of chance, a result of mathematical necessity, or the expression of something even more mysterious may never be revealed to us. But as we measure, model, and marvel at their precision, we continue to unravel, one number at a time, the hidden logic that holds everything in balance. The equation that explains everything. Does a theory of everything exist? For centuries, scientists have searched for patterns that reveal the hidden order behind the complexity of the universe. Each new unifying theory, from Newton's gravity to Einstein's relativity, has shown that simple laws can explain vast and seemingly chaotic behaviors. This pursuit of ultimate simplicity, of a single fundamental equation that explains all forces, particles, and phenomena, is known as the search for a theory of everything. It is an ideal as old as science itself, a single set of mathematical principles that completely describes reality, from the infinitely small to the infinitely large, from the birth of stars to the motion of electrons, from the curvature of space-time to the most subtle quantum entanglements. But does such a theory really exist? Today we have two foundational pillars that support our understanding of the universe. On one side, general relativity, formulated by Albert Einstein in 1915, describes gravity as the curvature of space-time caused by the presence of mass and energy. This theory works flawlessly on macroscopic scales, planets, galaxies, black holes, and the expansion of the universe itself. On the other side, we have quantum mechanics, and more specifically, the standard model of particle physics, which describes with extraordinary precision the interactions between fundamental particles and the three non-gravitational forces: electromagnetism, the strong nuclear force, and the weak nuclear force. The problem is that these two theories, as successful as they are in their respective domains, are incompatible when applied simultaneously, such as in extreme situations involving black holes or the origin of the universe. The theory of everything, therefore, needs to accomplish something extraordinary: to reconcile general relativity with quantum mechanics. This means creating a mathematical framework in which gravity is quantized. In other words, treated as a force that, like the others, arises from the exchange of elementary particles, hypothetically called gravitons. This would lead us to a unified description of the four fundamental forces of nature. Several proposals have been made over the last century to achieve this goal, the most prominent being string theory and loop quantum gravity. String theory suggests that fundamental particles are not points, but tiny vibrating strings, whose different vibrations correspond to the different particles we observe. This theory requires the existence of extra dimensions, 11 in total, and proposes that all the physics of the universe results from the geometry of these compactified dimensions. While mathematically rich, it still lacks experimental confirmation. Loop quantum gravity, on the other hand, attempts to directly quantize space-time, suggesting that it is made of discrete units, like a cosmic fabric composed of tiny grains. Both approaches have made progress and face challenges, and neither has yet delivered the long-awaited final equation. The idea of a theory of everything goes beyond physics. It represents a philosophical ambition, the belief that the universe, no matter how complex it may seem, is governed by an underlying logic that is simple and elegant. Einstein believed this deeply and spent decades, unsuccessfully, trying to unify gravity with electromagnetism. Many contemporary physicists share this desire. Others, however, question whether this quest makes sense. What if the universe is ultimately chaotic or plural? What if there is no single equation, but rather a landscape of possible solutions, as suggested by the multiverse? In some string theory-derived models, for example, there are more than 10 septindecillion possible mathematical solutions, that is, one followed by 55 zeros. Even if the theory of everything exists, it might be inaccessible. It may require such high energy to be tested that we will never be able to reach it. Or it could be hidden on scales so small that no conceivable instrument will ever reveal it. Still, the search itself has generated remarkable progress. In trying to unify the forces, physicists have developed more refined models, discovered hidden symmetries, revealed new particles, and even raised new questions about the nature of time, space, and reality. The theory of everything, if it is ever found, may be written in incredibly compact form, perhaps a single equation with only a few symbols. It would be the ultimate compendium of cosmic order, the key that unlocks all the doors of the unknown. But even if we never reach it, the effort to find it remains one of the noblest expressions of the human mind, the attempt to understand the whole, starting from the essential. The Fermi paradox. Where are all the aliens? On a quiet night near Los Alamos around 1950, physicist Enrico Fermi, Nobel Prize winner and one of the fathers of nuclear energy, was having lunch with fellow researchers when, during an informal conversation about flying saucers and possible extraterrestrial civilizations, he asked a simple and direct question that would echo for decades. Where is everybody? This question, which would become known as the Fermi paradox, encapsulates an enigma as perplexing as it is profound. If the universe is so vast, so ancient, and filled with trillions of stars hosting potentially habitable planets, why haven't we detected any clear signs of intelligent life beyond Earth? Why does the sky remain silent? The paradox arises from an apparent contradiction between the high statistical probability of intelligent extraterrestrial life and the complete lack of empirical evidence for it. In our galaxy alone, the Milky Way, there are estimated to be around 400 billion stars, at least 100 billion of which likely have planetary systems. Assuming that even a tiny fraction of these planets develop life and a smaller fraction evolves to become technologically advanced, the number of civilizations should be immense. And given that the universe is over 13 billion years old, many of them should have had ample time to arise, evolve, colonize their galaxies, or at the very least, send out detectable signals. Yet to this day, our radio telescopes detect only silence. One possible explanation for this silence is known as the Great Filter Hypothesis. This idea proposes that there is a barrier, or a series of barriers, in the evolutionary path of life that makes it extremely unlikely to become intelligent and capable of interstellar communication. This filter might lie in the past, Perhaps it's incredibly rare for life to emerge from non-life, or for multicellular organisms to evolve, or for intelligence to arise. Or the filter could be in the future. Perhaps all civilizations advance to a certain technological threshold and then self-destruct, fall victim to natural catastrophes, or lose interest in exploring the cosmos. If that filter is still ahead of us, then our current existence may be teetering on the edge of an inevitable fate. Other explanations are less grim. Perhaps we're looking in the wrong direction, using the wrong tools, or listening on the wrong frequency. Our methods, like the SETI project, are based on human assumptions about how alien civilizations might try to communicate. Perhaps extraterrestrials use completely different methods of transmission, exotic particles, gravitational modulation, or even quantum-entangled communication. Perhaps they are active but deliberately avoiding contact. The so-called galactic zoo hypothesis, where Earth is observed from a distance as a natural experiment. It's also possible that some civilizations are so advanced that we fail to recognize their signals, or that they exist in parallel realities beyond our perception. There is also the possibility that intelligent life is self-limiting. A civilization may reach a high level of technological development and then turn inward, exploring virtual realities, simulated universes, or forms of existence that don't involve space colonization. In this case, the absence of signals doesn't mean the absence of life, but rather the absence of intent to be noticed. The silence would then be a product of cosmic introspection. The universe may be full of conscious minds, but all in retreat. Even more provocative hypotheses exist. What if we are the first? Perhaps Earth is the initial spark of conscious life in the observable universe. Or conversely, what if we are the last, the only remnants after successive extinctions? Or perhaps we are inside a simulation where the absence of other civilizations is a deliberate limitation in the code. Each of these ideas forces us to rethink our assumptions about time, existence, and purpose. The Fermi paradox remains unsolved, but its power lies precisely in its ability to raise questions that transcend science and touch the foundations of philosophy. In asking where everyone is, Fermi also compels us to ask, who are we? What is our role in such a vast and apparently empty universe? The answer may lie out there, in some distant star, in a forgotten frequency, in a signal we have yet to learn how to decipher. Or perhaps it is right here in the silence that surrounds us and that we are still trying to understand. The Drake equation and the estimate of advanced civilizations. In 1961, at the dawn of the space age, and during a peak in scientific curiosity about extraterrestrial life, astronomer Frank Drake proposed a formula that would become one of the most emblematic intellectual exercises in modern science, the Drake equation. Its goal was not to provide an exact answer, but to offer a logical and mathematical framework that would allow us to reflect, based on data and estimates, on the number of technological civilizations with which we might potentially communicate within our galaxy. The beauty of this equation lies in how it connects astrophysics, biology, sociology, and technology, transforming the mystery of the cosmos into a sequence of fundamental questions about life and its evolution. The Drake equation is composed of 7 multiplicative factors. It begins with the average number of stars formed per year in our galaxy, currently estimated at about 7 per year. It then considers the fraction of those stars that have planetary systems, something we now know to be extremely common thanks to decades of exoplanet discoveries. The third factor assesses the average number of planets per star system that could potentially support life. That is, those located in the so-called habitable zone, where liquid water can exist. Up to this point, observational data has allowed for reasonably reliable estimates. The next terms of the equation dive into murkier waters. They involve the fraction of these habitable planets where life actually arises, the fraction where life evolves into intelligent forms, and the fraction where such intelligent forms develop technology capable of emitting detectable signals into space. For each of these factors, science still lacks solid data, because so far we only have one confirmed example, Earth. However, research in synthetic biology, studies on the origins of life, and computer simulations are offering increasingly refined insights. Some suggest that life may arise relatively easily. Others argue that the transition to technological intelligence may be extremely rare. The final term of the equation may be the most decisive. the average length of time a civilization emits detectable signals. This factor heavily influences the equation's outcome, because even if thousands of civilizations have existed throughout the galaxy's history, if each lasted only a few centuries before going extinct or falling silent, the chance of being active and visible at the same time is very low. On the other hand, if some civilizations manage to survive for tens of thousands or even millions of years, then the galaxy could be teeming with scattered consciousnesses, simply waiting for us to discover the correct way to listen. Based on conservative estimates, some scientists have reached figures like 10, 100, or even 10,000 active civilizations in the Milky Way right now. More skeptical estimates, assuming strict filters in the transition from life to intelligence, reduce that number to fewer than one, implying that we might indeed be unique. The Drake equation doesn't tell us which of these views is correct, but it forces us to confront the probabilities, to acknowledge the vastness of the unknown, and to consider ourselves not as the center of the universe, but as a statistical variable in a cosmic model. More than a scientific tool, the Drake equation is a cosmic meditation. It transforms the starry sky into a web of possibilities, where each star is a question and each planet a chance. It compels us to face deep time, to reflect on the longevity of human civilization, and to imagine what may have happened or what might still arise among the stars. Even if we never find an alien civilization, the simple act of contemplating their existence already changes us. The Drake equation teaches us that searching for life out there is also a way of understanding the value and rarity of life in here. The Kardashev scale, types of civilizations in the universe. In 1964, Russian astrophysicist Nikolai Kardashev proposed a bold and visionary method for classifying technological civilizations on a cosmic scale. Instead of using cultural, social, or philosophical criteria, Kardashev chose an objective, universal, and measurable parameter: the amount of energy a civilization is capable of harnessing and controlling. Thus, the Kardashev scale was born, a simple yet profound framework that imagines technological progress as a growing expansion in the ability to capture energy, from a home planet to the entire observable universe. Though it may sound like science fiction, this scale is still used today in serious studies of astrobiology, futurism, and SETI, as it helps us envision not only who we might find in the cosmos, but also what we might become. The original Kardashev scale is composed of three primary levels. A Type I civilization can utilize all the energy available on its home planet. This includes solar, wind, nuclear, geothermal, and chemical energy, essentially all the power that reaches or emanates from Earth. It's estimated that this corresponds to around 10 quadrillion watts. For comparison, modern humanity consumes approximately 18 trillion watts, placing us, according to physicist Carl Sagan's calculations, at about 0.73 on the Kardashev scale. In other words, we are still a subtype 1 civilization, slowly moving in that direction. Type 2 civilization would be able to harness and use the total energy output of its parent star. In our case, that would be the Sun, roughly 400 quintillion watts, a colossal amount far beyond humanity's current capabilities. Achieving this feat might involve constructing megastructures such as a Dyson sphere, a shell or swarm of satellites around a star, capable of absorbing most of its radiation. Although these remain theoretical, astronomers have searched for signs of Type 2 civilizations by observing unusual light fluctuations from stars, as with the famous Tabby's star, which drew global attention for its atypical behavior. A Type 3 civilization, in turn, would be capable of controlling the energy of an entire galaxy. This implies using billions of stars as energy sources through technologies so advanced they border on the unimaginable. It would be as if the entire Milky Way, with its 300 billion stars, were transformed into a cosmic power plant. Such a civilization would have achieved levels of engineering, information processing, and intelligence that could make their actions indistinguishable from natural phenomena, like stellar explosions or gamma-ray bursts. Some scientists speculate that if such civilizations exist, they may have left behind traces in thermal signatures, reorganized star systems, or even artificially manipulated black holes. Modern expansions of the scale include even more ambitious categories, such as Type IV civilizations, capable of manipulating the energy of the entire observable universe, and type 5, which would control multiple universes, purely speculative but useful for contemplating the limits of intelligence and technology. Each step up the scale represents a colossal leap in energy capacity, organization, and ambition. The transition between levels is not linear, but exponential. For this reason, even reaching Type 1 from our current position requires massive advances in sustainability, planetary engineering, and social stability. The Kardashev scale invites us to view human progress not as a fixed endpoint, but as an open-ended journey. It reveals that the cosmos may harbor intelligences so ancient and powerful that they defy our comprehension. And at the same time, it inspires us to imagine what we might build if we survive today's challenges and learn to cooperate on a global scale. To reach Type 1, we must first resolve our internal crises: clean energy, climate change, lasting peace. The road to the stars begins within ourselves. Type 2 and 3 civilizations. Is it possible to manipulate stars and galaxies? The idea that a civilization could one day directly manipulate entire stars or even galaxies may seem, at first glance, like an exaggeration born of science fiction. However, when we analyze technological progress as a continuum based on the capacity to collect and use energy, as proposed by the Kardashev scale, it becomes plausible to imagine that a sufficiently advanced species could achieve such feats. Type 2 and the 3 civilizations, unlike us, would not be limited to the energy consumption of a single planet. They would operate with technologies so vast that the cosmos itself would become their domain, altering stars like chess pieces on a cosmic board and rearranging galaxies like architects on a stellar scale. A Type 2 civilization, having mastered its star's energy, would be capable of performing feats we can currently describe only in theoretical terms. The most famous of these technologies is the Dyson sphere, a hypothetical structure composed of thousands, perhaps millions of satellites or solar collectors orbiting a star and capturing nearly all of its radiant energy. A complete sphere would be unstable, but a Dyson swarm, a dispersed array of independent orbiting structures, is considered more plausible. The goal would be to harness the energy output of a star like the Sun, which continuously emits around 400 quintillion watts. That's more than 20 billion times humanity's current energy consumption, enough to power megastructures, artificial worlds, or even vast simulated civilizations. Furthermore, a Type 2 civilization could alter its star's behavior. This could include controlling solar activity, preventing supernova formation, redirecting coronal mass ejections, or even moving the star through the galaxy using large-scale gravitational propulsion. This concept, known as stellar propulsion, appears in theoretical models like the Shkadov thruster, which uses a massive, partially concave mirror to unbalance solar radiation and generate thrust. Over millions of years, it could potentially move the entire star system. Leaping to a Type 3 civilization, the scale of control expands to include all the stars within a galaxy. This would mean not only capturing energy from multiple stars simultaneously, but also rearranging them, fusing them, isolating them, or using them as propulsion sources for mobile structures. Imagine trillions of solar systems transformed into raw material for intelligent machines, advanced computation, or stellar-scale habitats. Such a civilization would likely transcend biology as we know it, existing as distributed intelligence, cosmic neural networks, or artificial entities operating over millions of years. Theoretical galactic engineering includes ideas like galactic Dyson spheres, orbital rearrangements of stellar systems to create massive computational structures, such as the so-called Matryoshka brain, or even the construction of artificial black holes for energy and computational purposes. Some suggest a Type 3 civilization could store its consciousness in accretion disks around black holes, where time dilates and information density approaches physical limits. The big question is, why haven't we observed any of this? Perhaps because such civilizations are incredibly efficient at hiding, using undetectable radiation or operating passively, or perhaps we're underestimating the subtlety of what we're looking for. Even Dyson structures should emit residual heat, a signature in the infrared spectrum, and telescopes like WISE have searched for such evidence. So far, we've found no clear signs of stellar or galactic engineering. This may suggest that such civilizations are rare, have already gone extinct, or simply lack the desire to visibly expand. What Type 2 and 3 civilizations teach us, then, is that the universe theoretically allows for levels of technology and organization far beyond our current imagination. And by contemplating that possibility, we also look toward humanity's future. Will we be capable of taking the first step toward Type 1? Will we have the stability, cooperation, and long-term vision needed to even begin that journey? The answer remains open, echoing among the stars. The silence of the cosmos. Why does the universe seem so quiet? When we gaze up at the night sky, what strikes us most is not only the vastness of the stars, but the silence that surrounds them. No signals, no patterns, no clear messages coming from beyond. Despite billions of galaxies, trillions of planets, and billions of years of cosmic time, there is no direct indication of intelligent life beyond Earth. This silence is so profound that it has become in itself one of the greatest questions of modern science. The absence of signals amidst such immensity leads to a disturbing question. Why does the universe, with all its potential, seem so quiet? This silence becomes even more enigmatic when we remember that we have already sent signals into space. From early radio broadcasts to intentional transmissions like the famous Arecibo message in 1974, humanity has been shouting into the cosmos for decades. If other civilizations are doing the same, or did so at any point in the last few million years, we should theoretically have detected something by now. Yet hundreds of radio telescopes around the planet have not picked up a single artificial emission that stands out from natural cosmic noise. Projects like SETI, which systematically monitor the sky, have also returned nothing but silence. One possible explanation for this silence is time. The universe is over 13 billion years old, while human technology for emitting and receiving radio signals has existed for just over a century. It may be that technological civilizations last only a few thousand years, a mere blink on the cosmic scale, and that the window of their existence and ours simply doesn't overlap. Perhaps many civilizations have already come and gone before we were able to detect them, and others are yet to arise in the distant future. From this perspective, the universe isn't silent. It's just out of sync with us. Another hypothesis is intentional isolation. Advanced civilizations might adopt a policy of non-interference, choosing not to emit detectable signals or actively masking their presence using technologies that absorb or deflect radiation. This is known as the galactic zoo hypothesis, which suggests that Earth is treated like a natural preserve, observed from afar. According to this theory, the silence is not natural but deliberate, a kind of invisible curtain drawn by older, wiser species who avoid contact with emerging civilizations like ours. There's also the possibility that the technology we use to listen to the universe is obsolete. Interstellar communication may occur in ways we don't yet understand or even imagine, such as signals based on quantum entanglement, gravitational manipulation, or through channels that defy conventional space-time. In that case, the silence would merely be a limitation of our perception, not a true absence of voices in the universe. Finally, it's possible that we are a rare exception. Perhaps life is common, but technological intelligence is extraordinarily unlikely. Or perhaps intelligence, once achieved, almost always self-destructs, through wars, environmental collapse, or simply by losing interest in external communication. In this scenario, the universe is not empty, but full of accumulated silences, of extinct civilizations, of echoes of voices we can no longer hear. The silence of the cosmos is not merely an absence, it is an invisible presence that challenges us, intrigues us, and forces us to reflect on our own position in time and space. Each signalless night reminds us that for now we are alone, or at least unanswered, and that, as unsettling as it may be, is also an invitation to keep listening, to evolve patiently, and to understand that perhaps the first sound to echo across the universe will be our own. The mystery of anomalous signals like the WOW signal. On the night of August 15, 1977, something unusual captured the attention of scientists working on the SETI project, which at the time was using Ohio State University's Big Ear radio telescope to scan the skies in search of signals from intelligent life. During a sweep through the constellation Sagittarius, the system recorded a sudden burst of radio waves at a very specific frequency, 1420 megahertz, the same as the natural emission of hydrogen atoms, considered a logical interstellar highway for cosmic communication. The signal lasted exactly 72 seconds, the maximum detection time of the telescope, and it never repeated. When astronomer Jerry Amon analyzed the data and saw the intensity of the spike, he circled the reading and wrote next to it in astonishment, "Wow!" Thus was born one of the greatest enigmas in the search for extraterrestrial life, the famous WOW signal. What made the WOW signal so fascinating was its apparent artificiality. It didn't resemble random cosmic noise, such as pulsars or solar flares, nor did it show characteristics typical of terrestrial interference. Its frequency was stable, concentrated, and perfectly aligned with a region of the spectrum considered ideal for interplanetary communication. The lack of modulation or repetition made it difficult to determine whether it was a message, but the mere fact that it appeared so clearly in a quiet band of the universe ignited hope among scientists. Since then, countless attempts have been made to relocate the signal. Modern radio telescopes have scanned the same region of the sky repeatedly, but the signal has never been detected again. This lack of repetition is one of the most frustrating aspects for scientific analysis, as it prevents empirical verification and reduces the likelihood of confirmation. As a result, many researchers have considered alternative causes. Some hypotheses involve satellites, comets, or reflections of terrestrial signals, but none have managed to reproduce all the observed characteristics of the WOW. One of the most debated explanations came decades later, when two astronomers suggested the signal could have been caused by a hydrogen cloud detached from a comet, specifically Comet 266P Christensen, which was near that region of the sky in 1977. However, this explanation has been widely contested, since comets typically emit in broad and diffuse frequencies, not with the precision and intensity recorded in the signal. Still, in science, natural hypotheses are always considered first, even when they are not fully satisfying. The WOW signal also raised questions about the method itself for searching for extraterrestrial intelligence. Perhaps artificial signals are not continuous, but rather single pulses, like flashlights blinking in the dark. Perhaps the time between transmissions is so long that we miss most of them, or perhaps the signals are encoded in such a way that they appear as ordinary noise to our detectors. This line of thinking led to the development of more sensitive and sophisticated projects, such as Breakthrough Listen, which now monitors billions of frequencies simultaneously using artificial intelligence algorithms capable of detecting subtle patterns in cosmic noise. Even so, the WOW remains unique. It serves as a reminder that the universe may occasionally whisper something unexpected, and that our listening, no matter how careful, is still just beginning. The signal is a metaphor for the Fermi paradox itself, a flash of something perhaps grand, perhaps accidental, that stirs our curiosity, but refuses to offer easy answers. We do not know if the WOW was an instrumental error, a rare physical phenomenon, or a distant greeting from a civilization that no longer exists. What is certain is that the WOW signal marked an entire generation of scientists and astronomers. It turned a sheet of paper filled with numbers into a symbol of all that we still do not understand. In its brevity, it condensed the mystery of the cosmos, a question written across the sky, silent and solitary. And to this day, among all the signals ever recorded, it remains the most intriguing, the most iconic, and perhaps the loneliest of them all. The Moon. Origin, composition, and oddities of our satellite. The Moon is the closest celestial object to Earth, our eternal companion in the sky, visible to the naked eye on most nights. Despite its visual familiarity, it harbors mysteries that continue to challenge scientific understanding. Its origin, composition, and behavior exhibit such unique characteristics that for decades astronomers and planetary geologists have sought increasingly refined theories to explain what this celestial body truly is. A body that influences tides, stabilizes Earth's rotational axis, and has fascinated civilizations since time immemorial. What we know about the Moon is substantial, but what remains unknown reveals how much it continues to be an active frontier in planetary science. The most widely accepted hypothesis for the Moon's origin is the giant impact model. According to this theory, about 4.5 billion years ago, an object the size of Mars, called Theia, collided with the forming Earth. The impact was so intense that part of Earth's mantle and fragments of the impacting object were ejected into orbit, forming a disk of debris that, over millions of years, coalesced into the Moon. This hypothesis is supported by evidence such as the isotopic similarity between lunar and terrestrial rocks, especially in oxygen-17. However, the model still faces challenges, such as the absence of clearly identifiable Theia material in the lunar samples returned by the Apollo missions, suggesting the Moon might be composed mostly of terrestrial material. From a geological perspective, the Moon has a surprisingly complex internal structure. It features a crust, mantle, and core, like Earth, but with different proportions and compositions. Its core, composed of partially molten iron, is small relative to its overall volume. The mantle contains minerals such as olivine and pyroxene, and is the region where the lunar Maria formed. Vast plains of solidified basalt visible from Earth as dark spots. The crust is thick, rich in anorthosite, and marked by impact craters dating back billions of years. These impacts created giant basins and spread regolith, a layer of fine dust and rock fragments that covers the lunar surface. There are peculiarities in the Moon's behavior that continue to intrigue scientists. One of them is synchronous gravitational resonance. The Moon rotates on its axis in exactly the same time it takes to orbit Earth, which is why we always see the same face. The far side, revealed only through space probes, is far more mountainous and less covered by lava seas than the near side. The reason for this asymmetry is still under active investigation. Another remarkable anomaly is the presence of mass concentrations, or mascons, regions with slightly higher gravity beneath impact basins, suggesting dense structures are buried under the surface. The Moon also exhibits a curious phenomenon known as moonquakes. During the Apollo missions, astronauts placed seismometers on the lunar surface which detected seismic activity. Some of these moonquakes are caused by meteor impacts, others by thermal variations, and some deep seismic events still have unknown origins. Despite lacking tectonic plates like Earth, the Moon is geologically active on a small scale, offering opportunities to study its internal thermal evolution and the dynamic history of the Earth-Moon system. There are also unresolved questions about the presence of water on the Moon. For decades it was believed to be completely dry. However, recent missions such as India's Chandrayaan-1 and NASA's L-Cross detected signs of water ice in permanently shadowed craters near the lunar poles. Additionally, traces of hydroxyl were found in surface minerals, suggesting the Moon may have retained water or that solar processes continually form it. This significantly alters our understanding of lunar history and opens new possibilities for future crewed missions and sustainable lunar bases. The Moon is more than a natural satellite. It is a time capsule, a silent witness to the formation of the solar system, and a natural laboratory for studying geology beyond Earth. Its ongoing study reveals how much there is still to learn about it, and by extension, about ourselves. Each new mission, each new piece of data deepens the mystery and expands the fascination. The Moon remains at once near and unreachable, simple and complex, clear in its presence, yet obscure in its origins. The enigma of rogue planets and solitary interstellar systems. Among the stars, there aren't only neatly ordered planetary systems like our own. There are also solitary wanderers, sunless worlds, orphaned planets that drift through the darkness of interstellar space, bound to no star. These are the so-called rogue planets, celestial bodies that do not orbit a sun, but instead roam the cosmos along independent trajectories, like cosmic castaways adrift after gravitational catastrophes. The existence of such worlds radically alters our perception of the universe's structure and the minimum conditions under which a planet can exist. They are both common and profoundly mysterious. The discovery of rogue planets became possible through techniques like gravitational microlensing, a phenomenon predicted by Albert Einstein, in which the gravity of a massive foreground object bends the light of a background object. When a planet passes between us and a distant star, its gravity can momentarily focus the light of that star, creating a measurable brightening. This detection method allows scientists to identify objects that do not shine or reflect starlight, and thus would be invisible to traditional observational techniques. Thanks to these tools, astronomers have already detected multiple rogue planet candidates, and it is estimated that the Milky Way alone may harbor billions of them, perhaps even more than the number of planets orbiting stars. These solitary worlds may have originated in violent events during the early stages of planetary formation. In the birth of stellar systems, gravitational interactions between young planets can lead to collisions or ejections. A newly formed planet might be flung from its orbit by tidal forces or close encounters with other massive bodies. Once it escapes the pull of its parent star, it continues its journey through the galaxy, cold and dark, but still retaining mass and structure. In other cases, these planets may have formed independently, like failed stars made primarily of gas, but without enough mass to ignite nuclear fusion. The idea of planets drifting without a sun raises fundamental questions about habitability. At first glance, such worlds lacking stellar light would seem frozen and inert. However, some simulations suggest that rogue planets could retain enough internal heat to maintain subsurface liquid oceans, especially if they have thick hydrogen-rich atmospheres that act as thermal insulators. Additionally, geothermal processes such as radioactive decay or internal pressure could provide enough energy to sustain microbial ecosystems in environments similar to the icy moons of Jupiter and Saturn. This opens the theoretical possibility of UFO life on sunless worlds, a notion that challenges traditional criteria for habitability. Another intriguing aspect is that rogue planets may occasionally capture moons or even be recaptured by stars on future trajectories. A solitary planet passing close to a star might be pulled into orbit by its gravity. This raises the possibility of non-linear planetary systems where bodies enter and leave stellar orbits over billions of years. It also suggests that some of the exoplanets we observe today may have once been nomads, with dynamic histories that defy the simplicity of current models. The observation of solitary systems, consisting of a massive planet, possibly with moons, traveling through space without a star, marks a new frontier in astronomy. These quiet, dark worlds may carry within their structure the history of disrupted stellar systems, chaotic cosmic encounters, or rare formations within the densest regions of molecular clouds. They remind us that the universe doesn't adhere solely to neat patterns. It also harbors the unpredictable, the marginal, the unconventional, and that life, if it exists, may have found ways to flourish even in stellar exile. Super-Earths and ocean worlds, planets that may harbor life. The search for life beyond Earth has traditionally focused on finding planets similar to our own, in size, temperature, and composition. However, over the past few decades, astronomical discoveries have greatly expanded that horizon. Two types of exoplanets have emerged as particularly promising for habitability: the so-called super-Earths, rocky planets larger than Earth, and ocean worlds, planetary bodies almost entirely covered in water. Both represent fascinating possibilities for harboring life, although under conditions that may differ significantly from those we know. Super-Earths are exoplanets with masses ranging from about 2 to 10 times that of Earth. Despite their name, not all are simply bigger Earths. Some may have thick atmospheres and hostile surfaces, resembling mini-Neptunes. However, many others exhibit densities and compositions consistent with rocky worlds, suggesting the presence of solid crusts, volcanism, and tectonic activity. Their higher gravity can help retain stable atmospheres over billions of years, shielding the surface from cosmic radiation and allowing for long-term climate cycles. This makes them compelling candidates for supporting complex biospheres, possibly even more resilient than Earth's, provided the local chemistry is favorable. Moreover, due to their size, super-Earths tend to maintain geological activity for longer periods, a key factor in supporting habitability. Plate tectonics, internal heat, and continuous volcanism help recycle life-essential chemical elements such as carbon and nitrogen. These processes also sustain magnetic fields, which protect planets from harmful solar particles. In older star systems, where Earth might have cooled and lost tectonic activity, a super-Earth could still sustain a dynamic, habitable environment. At the same time, ocean worlds present another exciting frontier. These planets are composed mostly of water, with oceans that may stretch hundreds of kilometers deep, lacking continents or exposed rocky features. Some may have dense, warm atmospheres, while others might have icy outer layers covering vast liquid oceans beneath, heated internally or through tidal interactions with nearby stars or moons. In both cases, The abundance of liquid water makes them prime environments for the development and maintenance of life. A well-studied example is the TRAPPIST-1 system, where several Earth-sized exoplanets orbit a red dwarf star at close enough distances for temperatures to allow liquid water. Models suggest some of these planets may be water-rich, with proportions far exceeding those of Earth. In such worlds, life might emerge deep in the oceans, shielded from stellar radiation by kilometers of water, under conditions akin to Earth's deep-sea hydrothermal vents, which host biologically rich communities. The main challenge in assessing the habitability of these planets is their distance. Even the nearest candidates lie dozens or hundreds of light years away. Detecting atmospheres and potential biosignatures on such worlds requires extremely sensitive instruments, like the James Webb Space Telescope and its future successors. Nonetheless, significant progress is underway. Spectroscopic observations may reveal gases such as oxygen, methane, water vapor, and carbon dioxide, indirect but compelling signs of possible biological processes. Super-Earths and ocean worlds expand our definition of what it means to be habitable. They demonstrate that life may emerge and thrive under conditions unlike those on Earth, and that the universe may be filled with environments where organic chemistry followed its own unique evolutionary paths. These planets are not just scientific targets, they are mirrors of possibility. In studying them, we not only search for life out there, but also come to better understand the conditions that make our own world so uniquely precious. Life based on alternative chemistries, silicon, ammonia, and exotic hypotheses. For a long time, science has searched for extraterrestrial life based on a single template, life as we know it, carbon-based, dependent on liquid water, and governed by a specific biochemistry that operates within relatively narrow ranges of temperature and pressure. However, as we explore the universe and recognize its extreme diversity, it becomes increasingly plausible to imagine life forms that arise under radically different conditions. This concept leads to the study of life based on alternative chemistries, organisms that, instead of following Earth's recipe, may have evolved from different elements and solvents such as silicon or ammonia. Carbon is indeed an extraordinary element. Its chemical versatility allows it to form complex and stable chains, creating the foundation for proteins, nucleic acids, and lipids. But it is not the only element capable of such complexity. Silicon, which lies in the same group as carbon in the periodic table, also forms 4 covalent bonds and can produce similar structures. This has led many astrobiologists to consider the possibility of a silicon-based biochemistry, especially in environments with higher temperatures, where organosilicon compounds might be more stable. However, silicon has limitations. Its molecules are generally less flexible and more prone to forming solids, making it difficult to support adaptable, self-replicating systems like those built on carbon. Another candidate is liquid ammonia, as a solvent for life, replacing water. Ammonia is abundant in various environments throughout the solar system, such as in the atmospheres of Jupiter and Saturn, and possesses properties that allow it to dissolve organic compounds. At much colder temperatures than Earth, liquid ammonia could support chemical reactions analogous to those in water, enabling the emergence of living structures. However, the low temperatures required to keep ammonia liquid significantly reduce the speed of biochemical reactions, which could make such life much slower or reliant on entirely different mechanisms. Beyond silicon and ammonia, there are even more speculative proposals. Some theories consider the possibility of life based on liquid methane, like in the lakes of Titan, Saturn's largest moon. In that cold, dark environment, where temperatures hover around -180 degrees Celsius, methane could act as a solvent, and complex organic compounds have already been detected in Titan's atmosphere. Although there is no direct evidence of metabolism or replication under such conditions, the presence of active, rich chemistry suggests that life might not be limited to the aqueous carbon model. Other hypotheses go further still. Some envision life forms that incorporate metallic compounds into their metabolisms, organisms that extract energy from magnetic fields, or even beings based on plasma or energy, potentially existing in extreme environments such as the upper atmospheres of cool stars or near black holes. Though such ideas lie well beyond our current ability to verify, they are valuable in expanding scientific imagination. In this sense, astrobiology is not only the search for life, but for every possible way matter can organize itself into adaptive complexity. It is important to remember that even on Earth, there are life forms that challenge the standard model. Extremophile, survive in extreme acidity, scorching temperatures, or complete absence of light and oxygen. This suggests that our very notion of what is habitable needs reconsideration. If life could emerge and persist in places we once deemed uninhabitable, why couldn't it arise in environments we still don't fully understand? The search for biosignatures on exoplanets must therefore take this potential chemical diversity into account, limiting our detection efforts to oxygen and methane as the only indicators of life risks becoming a form of scientific myopia. The universe, in all its vastness, may be full of exotic biospheres that do not emit the signals we expect. And it is precisely this challenge, searching for the unknown with tools we are still learning to use, that makes astrobiology one of the most fascinating sciences of our time. Consciousness in the universe. Could it be a fundamental force? Consciousness is perhaps the greatest mystery in modern science. Despite significant advances in neuroscience, physics, and philosophy, we still do not know exactly what it is, where it comes from, or why it exists. What we do know is that it is undeniably present, in us, in our thoughts, in our perception of the world, and in our ability to reflect on the universe itself. But when we look outward into the cosmos and examine the matter that composes it, a profound question arises. Is consciousness merely a byproduct of biological complexity, or could it be a fundamental property of reality itself, like space, time, and energy? For some theorists, consciousness is an epiphenomenon, a secondary effect of neural activity in sufficiently complex brains. In this view, consciousness arises simply from matter organized in the right way, such as in biological or even artificial neural networks. While this explanation is widely accepted, it still faces a central unresolved issue, the so-called hard problem of consciousness, as formulated by philosopher David Chalmers. He asks how and why specific physical processes in the brain give rise to subjective experiences, feelings, sensations like color, pain, pleasure, or thought. To this day, no scientific theory can fully explain that leap from physical to experiential. This gap has opened the door to more audacious proposals, such as panpsychism, which suggests that consciousness is a fundamental property of the universe, present in some form in all matter. Like mass or electric charge, consciousness would not be something that emerges. It would already be there in some minute degree, even in subatomic particles. As structural complexity increases, this property expresses itself in more sophisticated forms, culminating in conscious beings like ourselves. Though controversial, this idea is gaining attention among physicists and philosophers seeking to unify quantum mechanics, information theory, and neuroscience. Another speculative but thought-provoking approach is ontological idealism, which flips the conventional logic. Consciousness does not arise from matter. Rather, matter emerges from consciousness. According to this view, the physical universe is a manifestation, an external reflection of a deeper mental reality. This perspective echoes ancient philosophical traditions, both Eastern and Western, including thinkers like Berkeley and Schopenhauer. In modern physics, certain quantum experiments that highlight the role of the observer in determining particle behavior have revived this debate. If reality only manifests when observed, what role does consciousness play in that process? Cosmology also contributes to the puzzle with the anthropic principle, which suggests that the laws of the universe seem finely tuned to permit the emergence of conscious life. The cosmological constant, the electron's charge, the proton's mass, all these parameters have incredibly precise values that, if altered slightly, would make life impossible. This leads us to wonder whether consciousness is merely an accidental byproduct of these parameters, or whether it plays some causal or structural role in the very architecture of the cosmos. In one of the more radical interpretations, proposed by physicist John Wheeler, the universe is participatory. It requires conscious observers to fully exist. Finally, new ideas are emerging at the intersection of neuroscience and theoretical physics, such as integrated information theory, which attempts to quantify a system's level of consciousness based on its ability to generate and integrate information. This approach aims to create a measurable model of consciousness that could apply not only to human brains, but also to artificial intelligence and alternative biological systems. Though still in its early stages, such efforts represent science's attempt to engage with one of the most subjective and metaphysically charged concepts imaginable. Consciousness, unlike traditional physical forces, cannot be detected by instruments or direct measurements. Yet it is undeniably real. It is the starting point of all experience and the necessary condition for the very concept of universe to make sense. Whether as a product of matter or as the foundation of existence, consciousness remains at the heart of the mystery, a light within that illuminates not only the outer world, but also the abyss of the unknown. And perhaps one day, to understand consciousness will be to understand the universe itself. The observable universe versus the real universe. What can't we see? When we look up at the night sky, we're seeing only an infinitesimal fraction of the cosmos. Even with the most advanced telescopes ever built, equipped with infrared, microwave, and radio wave sensors, our cosmic vision is confined by an unbreakable limit, the so-called observable universe. This term refers to everything we can detect, directly or indirectly, based on the light and information that has had time to reach us since the beginning of the cosmos. But this is not all that exists. Beyond this accessible bubble of information may lie an even greater expanse, perhaps infinite, referred to as the real universe, a realm completely beyond our reach. The observable universe has a radius of about 46 billion light-years under, when accounting for the expansion of space since the Big Bang. That gives it a diameter of roughly 92 billion light-years, filled with trillions of galaxies, quadrillions of stars, and an inconceivable amount of matter and energy. Yet all of that represents only what we can see. Because light travels at a finite speed and the universe has a finite age, there are regions whose light has not yet, and may never, reach us, especially if cosmic expansion continues to accelerate due to dark energy. These regions are forever beyond our cosmic horizon. Like lands hidden behind a mountain we will never be able to climb. The real universe could be dozens, hundreds, or even infinitely larger than the observable one. There is no evidence that space ends just beyond our field of vision. In fact, measurements of the universe's geometry suggest it is spatially flat, which in cosmological terms implies it could stretch on forever. Within this hypothetical vastness, there may be copies of the Milky Way, radically different galaxies, or even regions with distinct physical laws, depending on which interpretation of cosmic origins one accepts. This idea aligns with some versions of the up-inflationary multiverse, in which bubbles of space-time expand and separate eternally, forming independent universes with differing fundamental constants. Even within the observable universe, there are severe limitations to what we can detect. A large portion of the matter in the cosmos is invisible, known as dark matter, which neither emits, reflects, nor absorbs light. Its existence is inferred through the gravitational effects it exerts on galaxies and galaxy clusters. It's estimated that about 85% of the universe's total mass exists in this dark, completely opaque form. Added to this is dark energy, an even more enigmatic component that makes up roughly 70% of the universe's total content, acting as a repulsive force that accelerates cosmic expansion. Altogether, this means that everything we can see, stars, planets, gas, dust, represents only 5% of what actually exists. We're also blind to the universe's earliest period, the first 380,000 years. Before the formation of the cosmic microwave background radiation, the universe was so hot and dense that light couldn't travel freely. This so-called opaque era is permanently hidden from direct observation via light. Only primordial gravitational waves, if ever detected, could carry information from that initial phase. Likewise, cosmic regions obscured by dust, black holes, and dense plasma remain invisible to traditional observation methods, requiring indirect techniques for study. The contrast between the observable universe and the real universe serves as a reminder of our condition. We are observers confined to a cosmic bubble, looking backward in time and trying to reconstruct a totality we may never fully experience. Yet this limitation is not a weakness. It is a triumph of scientific ingenuity. We have mapped the cosmic structure, inferred the presence of the unseen, and built mathematical models to speculate about what may lie beyond the horizon. This journey through the invisible cultivates both humility and curiosity, powerful forces that have driven science forward since the first human gazes into the night sky. The greatest mystery: why is there something rather than nothing? Of all the questions the human mind has ever dared to ask, none seems more fundamental or more impenetrable than this. Why is there something rather than nothing? This question stretches across centuries like a philosophical and scientific abyss. It doesn't seek to understand what the universe is, how it began, or what its fate may be. Instead, it interrogates the very existence of existence. Why is there space, time, energy, matter, physical laws, consciousness, instead of absolute silence, an eternal and inert void? Though it may sound abstract or even metaphysical, this question regains force as we understand more about the origin of the cosmos and the limits of physical knowledge. In modern physics, the birth of the universe is attributed to the Big Bang, a violent expansion that occurred approximately 13.8 billion years ago. But the Big Bang does not explain why that beginning happened. It explains the how, but not the why. Many attempts have been made to answer this primordial absence, from cyclic cosmological models to multiverse theories generated by quantum fluctuations. One widely discussed idea is that the universe could have arisen spontaneously from the quantum vacuum, a kind of unstable nothingness where particle pairs constantly appear and cancel each other out. In this scenario, an energy fluctuation would have sparked the birth of the universe, with time, space, and physical laws emerging as properties of that event. However, even the quantum vacuum hypothesis doesn't escape the question: what gave rise to the quantum vacuum itself? What underlies the laws that allow these fluctuations? At this point, physics approaches the conceptual limits of scientific language. Some philosophers and cosmologists argue that absolute nothingness may be logically incoherent, and that something, existence itself, is the only possible condition. Others propose that existence doesn't require a reason. It simply is a brute fact without cause or purpose. Though intellectually unsettling, this view aligns with certain interpretations of quantum mechanics, where randomness and indeterminacy define the universe at its most fundamental levels. There are even more speculative interpretations, such as the idea of the universe as a mathematical event, emerging inevitably from the combinatorial possibilities of logical structures. Physicist Max Tegmark, for instance, has proposed that every possible mathematical structure exists, and our universe is just one among these self-realizing mathematical realities. At this point, science and philosophy intertwine, for the question of why existence exists touches the boundaries of metaphysics and fundamental logic. If the universe is just one among infinite possibilities, then perhaps its existence needs no justification, only observation. Yet this question takes on a new dimension when we include consciousness, because not only is there something, but that something includes beings who know it exists. The universe does not merely exist. It is known, reflected upon, and felt. This deepens the original mystery. If absolute nothingness would be simpler, more economical, more predictable, then why did reality manifest with such complexity, with galaxies, atoms, gravity, life, thought, and beauty? Is there some hidden principle of self-organization, an ontological necessity for being to triumph over non-being? In the end, perhaps this is one of those questions that cannot be answered in the way our minds desire. It may be an essential inquiry of consciousness itself, a way of expressing our awe at the everyday miracle of existing. And perhaps the true meaning of existence does not lie in the answer, but in the fact that there is someone, here and now, who can ask the question. For the absolute silence of nothingness contains no doubt, no wonder, no beauty. But the universe, with all its galaxies, particles, and awareness, does. And that in itself may be the most profound answer of all.